remote centers. Today is the third day and it is the first session. For this session, we have invited a chief scientist from CSIU, Center of Scientific Instrument Organization, and he will deliver his lecture on the optical sources. And during his lecture, he will demonstrate the sources of it. I hope you will gain the experience of a scientist compared to a teacher. His way of demonstration, speaking, discussion may be different compared to the teaching faculty. And I hope you will enjoy his rich experience in this field because they are the real practical people. So I hope you will enjoy. And Dr. Ahmed Nagar will be with us here. Though I am also a product of the CSIR, long back I was scientist at CG Pilani. Working in CSIR is totally different compared to the technical institutions. There is only experimental work. On the basis of experimental work, we define something. So I request Dr. Nagar take the seat and have two sessions today. He will discuss both optical sources and optical detectors, and he will demonstrate during this session. That's it.
Very good morning to you all. I am Ranjit Nagar from CSIU, Central Scientific Instruments Organization. This is the instrument lab of CSIR. I will be delivering some of the topics concerning to optical sources required for fiber optic communication. So, single and double surface emitting LEDs, which is SLED we call it, edge emitting LED, which is called EELED in short, and superluminescent LEDs, which is called SLD. Then LED characteristics, its modulation techniques, basic laser operation. Again, double heterostructure strip geometry laser. I mean, we want to enhance the functionality of laser, both in laser and LED. So we define heterostructures for that. Then distributed feedback laser, DBR laser, vertical cavity surface emitting laser, quantum well laser, in-fiber laser, ring fiber laser, then laser characteristics, and then modulation of laser, both direct and external. So these topics I will be covering during this next 1.5 hours. So the basics of emission of light, which is mainly from the optical sources, is governed by a principle, basic principle, which says that when an electron jumps from a lower energy band to the higher energy band and returns back, it emits in the form of it emits energy, or the excited energy in the form of a photon, which is governed by E is equal to h nu, which is called radiative recombination because of the holes and electron recombinations, and as heat, non-radiative recombinations. So either of the two techniques or principles applies when an electron jumps from a higher energy state to a lower energy state. So the emission of light in the form of a photon can take place either spontaneously, meaning by randomly, or it can be stimulated. That means it is governed by some rules, which we will be discussing, by the interaction of another photon having right energy level. For a spontaneous or stimulated emission to occur, energy must be supplied to boost the electron from its low energy state to a higher energy state. That means when I want to transfer these electrons from a low energy state to a higher one, I must supply some form of energy. Like say in case of a semiconductor LED or laser, we supply in the form of a electric current or electroluminescent, we call that phenomena. So the light energy can be derived through either heat, which is we call it as an incandescent light, we see in the form of a bulbs, tungsten bulbs, wherein the heat is converted to the light energy. Then again electrical discharge, like we see in deuterium, mercury, sodium lamps, the discharge produces the light energy. Then the electrical current, which is LED or laser diode. Then again bioluminescence, which is we call it as a firefly or the jugnu. It has some sort of an enzyme called luciferase, which interacts with a protein available within the body. The interaction creates a bioluminescence, and a form of a light emission is taking place. The optical sources, since we are discussing mainly on the fiber optic communications, so the optical sources suited to this particular topic is light emitting diode, which is SLED, EELED, SLD, semiconductor lasers, which I have discussed just now, DFB, DBR, vertical cavity, multi-quantum wave laser, in-fiber laser, fiber ring lasers. The requirement for such sources should be, because we are interacting with the fiber, because the light must be coupled to the fiber, the physical dimension of the light output or the source must suit the optical fiber geometry, which is around 125 micron for a single mode fiber. The cladding is of the order of 125 micron and 8 to 10 micron for the core geometry. That means the light energy must be coupled to the dimension of the core or cladding core basically. Then it must have a narrow radiation pattern. That means the beam width should be narrow. That again, the ability to directly modulate by varying driving current. That means I must modulate my information, my electrical signals or communication signal in the form of a varying the current of the laser or LED by directly modulating it. Then another one is fast response time. Adequate output power to couple into the optical fiber, because we want to have a long range communications. Narrow spectral width, that means because fiber is having a material and modal dispersions, chromatic dispersions, so the spectral width should be narrow so that this type of activity which is taking place in the fiber material can be minimized. Then the driving circuit issues, which we will be discussing, stability, efficiency, reliability and cost, they are the another parameters which we must consider while selecting the source. The basic LED operation is, it has a PN junction which acts as a active or recombination region. That means the electrons and holes, they recombine and produces the excess energy in the form of a light or a photon. And the photon is having a particular wavelength that is governed by the band gap energy of the PN junctions. So for this we bias this PN junction, forward bias. The electrons and holes recombine either radiatively, that means emitting light, the excess energy in the form of a photon, or non-radiatively. If they don't emit light, it is converted into the form of a heat. And this is the simplest LED operation. You can see the conduction band and the valence band. When you excite, when you provide energy to it, the valence band electrons, they jumps to the higher energy state electrons, conduction band, and when they fall back, they recombine and produces a photon. The band gap for this, say for 1 electron volt corresponding to 1 electron volts, it produces the emission corresponding to that wavelength. So the emitted wavelength depends on band gap energy. The transition takes place from any energy state in either band to any other state in the higher bands. The valence band and the conduction band, they are not discrete, they have some width. That means such a transition produces in number of wavelengths. Although a peak wavelength is there, but around that peak wavelength there will be a another wavelength emitting from it. That means it is a non-coherent type of emission, or we call it as a spontaneous emission, and the typical wavelength range is of the order of 80 nanometer or more. So we want to reduce this as far as possible through the structure of this LED, right? So the light emitting semiconductor, they are mainly aluminum, gallium, indium phosphide. The wavelength range is 0.61 to 0.68. Gallium arsenide, aluminum gallium arsenide, indium gallium arsenide, indium gallium arsenide phosphate. The wavelength range, you can see It ranges from 0.61 to 1.7 micron, and the corresponding band gap energy is also varying from 1.82 to the 1.35. So light emitted is at the site of the junction, the PN junction, or the recombination area, where the recombination of electrons and holes are taking place. That produces the light. You can see that the light produced at the junction in the diagram you can see is emitting it all the four directions. That means the light which I want to make use of to couple it to the fiber is only a small amount. The rest of the light is wasted or it has gone outside. So that means I must now confine this junction so as that I must emit the maximum light in one particular direction or in one particular area which I need to couple it to the outside world. So the amount of radiative recombination and the emission area within the structure is dependent upon the semiconductor materials used and fabrication of the device. LED emits incoherent light through spontaneous emission. Such emission, I call it as a spontaneous emission because it is random. And such type of devices are used in multimode systems. That means multimode fiber, where the number of wavelengths can be propagated and the bandwidth or the data rate is of the order of 100 to 200 megabits per second. The broad spectral width and the wide output pattern is suitable for the multimode fiber. The light source material, most of the semiconductor light source contain 3-5 ternary or quaternary compounds. One of them is gallium aluminum arsenide. The doping concentration, or the X, 1 minus X or aluminum X, is possible to control the band gap energy. That means I can now control the band gap of these materials by varying the X, and correspondingly the emission wavelength emitted from this is ranging from 800 to 900 nanometer, and the spectral width is around 20 to 40 nanometer. Another material is indium gallium arsenide phosphide, where X is ranging from 0 to 0.47 and Y is 2.2X. So here the wavelength range is around 920 to 1600 nanometer, and the spectral width is around 70 to 180 nanometer. So for 850 nanometer region, because we know that the fiber optics works in 3 domain area, group 1 which is around 850 to 900 region, another area is 1300 nanometer, another one is 1550 nanometer, where the dispersion or the material attenuation loss, they are less. So we need these sources only in these regions, in these wavelength regions. So corresponding to this, we devise our materials and then the band gaps so as to select the various wavelength and corresponding the spectral width. So now we discuss on the fabrication aspect of this. So you can see this PN junction. We have a P-type material, you have a N-type material, you have a gallium arsenide, both sides, which is both the materials are same, and then the D on the right side, you see the D defines the band gap or the area where the recombination is taking place, and the third picture on this side shows the refractive index profile, which shows that there is a slight increase in the refractive index at the point where the junction is there. That means the light is now confined, right? Like as a fiber, in case of a fiber, we have a core, we have a cladding. The core refractive index is slightly higher than the cladding. The light propagates in the core. Same way, the light is confined in the junction area through the refractive index profile, and then the light is not escaping on the two barrier or the P plus and N type material. So this guidance is governed by because of the high refractive index at the junction area. So what we demand now, LED should have a high radiance, light intensity. That means because I want to have a long range communication, long length communication, fast response time. That means I must modulate that the electrical current which is flowing through this for this PN junction should be modulated so that I can modulate it in a faster rate. And then high quantum efficiency, that means the current which I supply to that and the amount of light which it emits, that defines my efficiency of that. So that is the three, four parameters which governs for my communication systems. So this is for homojunction when the two materials, the P and N materials, are same. What we want that the wavelength range and the spectral width should be narrow. So what people have devised is the heterojunction. That means different materials, they are aligning with the P and N type materials, so that the index of refraction of the cavity and the width of the junction can be controlled, so that I can get only a light at the a narrow region of the junction. The index of refraction of the material depends upon the impurity used and the doping level. The heterojunction region is actually lightly doped with P-type material and has the highest index of refraction. The N-type material and the more heavily doped P-type material both have lower indices of refraction. That means it forms the outer barrier region. This produces a light pipe effect. That means the light is confined only on the recombination region or the junction region. That helps to confine the light to the active junction region, which is missing in homojunction material. So double or single heterojunction structure we produces, the people at the semiconductor labs have produces for generation of high quantum efficiency laser LEDs. So heterojunction, you can see in the diagram, you have a P-type indium phosphide, you have a N-type indium phosphide, and the junction region is N-type indium gallium arsenide phosphide. So when such a structure wherein you have different materials is fabricated, you can see the refractive index profile at the right hand side, that it shows that there is a large variation in the refractive index as compared to the ground level of that, which confine the more light at this point. So the carriers are confined, light is also confined. This is called single heterojunction because we are using one heterojunction at the barrier points. So we can configure this in the form of a double heterojunctions, where we can confine this refractive index profile to much narrow region. So heterojunction is junction between two different semiconductors with different band gap energies. The difference in band gap energies creates a one-way barrier. Charge carriers or electrons or holes are attracted over the barrier from the material of higher band gap energy to the one of the lower band gap energy, and this recombination produces the light output. So now we switch over to the double heterojunctions, where we want to confine this refractive index profile to a much narrower region. So when a layer of material with a lower band gap energy is sandwiched between layers of material with a higher band gap energy, a double heterojunction is formed. This is called a double heterojunction because there are two heterojunctions present, one on each side of the active material. The double heterojunction forms a barrier which restricts the region of the electron hole recombination to the lower band gap material, and this region is called active regions. You can see on the diagram, you have a N-type indium phosphide, you have a P-type indium phosphide, and the band gap energy on the N-type indium phosphide is 1.35 electron volt, whereas at the junction region it is 1 electron volt. That means the recombination at the junction region at the N-type indium gallium arsenide, wherein the electrons and holes, when they recombine, the band gap energy of 1 electron volts corresponding to a particular wavelength, which is h nu, is emitted. Now I can control this 1 electron volt through different mechanism by doping or by fabricating different band gap materials within that. You can see the refractive index profile of this semiconductor materials. N2 is around 3.2, the N1, which is at the active region, is around 3.5. That means the active region is around 3.5, that is higher refractive index, and the two on the other side, they have a lower refractive index. That means now the light energy which is produced right on the junction itself is confined to this region only because of the light pipe effect. So the valence band is at a higher energy state than the valence band of the adjacent N-type indium phosphide. You can see the electrons, when I push electrical current to this PN junction in the forward bias, the electrons jumps from the N-type indium phosphide to the junction of the n-type indium gallium arsenide, because the conduction band of that is slightly at a lower energy state. Same way, the holes on the p side, they are at a lower energy state than the active region, so they move to that, and the recombination takes place within that active region. So that defines my double heterojunctions. More structures is possible to confine my N1 region, which is the active region. So this is how the fabrication takes place. You have a active region, you can see on the diagram itself. You have an active region which is a strip type of geometry people have at the semiconductor labs have created. You have a two confinement layers, which is N-type indium phosphide, P-type indium phosphide, and then you have a P-type indium phosphide, and then we have a substrate and the metallic contacts. So the active region is only at the strip type geometry, which is now confined in one direction only. Earlier we have seen in the homojunction case, wherein the light output is from all the four sides. Now the light output is only two sides on a strip type. The other two are acting as a insulator to the light. So you say the electrons are attracted across the left hand junction from the N-type indium phosphide to the N-type indium gallium arsenide phosphide. Holes are attracted from the P-type indium phosphide to the N-type of that active region. Recombination takes place in the active region, which is very small region. The heterojunction allows to have a small active region where light is produced. The material in the active region has a higher refractive index than that of the material surrounding it. This means that a mirror surface effect is created at the junction, which helps to confine and direct the light emitted. Further improvement has been taking place, where you can see at the bottom of the refractive index profile that it has a staircase structure, where the active region is further confined to 0.3 micron only. Rather than in case of homojunction, which is much larger as compared to double heterojunctions. That means this recombination is taking place only at the 0.3 micron, and the light guiding or the carrier confinement layer is around 1 micron, and the interaction is of the electrons and holes are taking place only in this 0.3 micron, and the confinement is producing a large amount of light at this region only, rather than at the confined or on the all the four sides. So we need this light output to be confined and guide the light within the device. Within the device, the light must be confined and directed to the exit aperture, so that it can be directed into the fiber, which is done using insulating material silica to confine the active region and current path. The active region in a higher heterostructure has a higher refractive index. This junction forms a mirror layer, helps to confine the light to the active layer. For this region, the outer layers are often called as confinement layer. Now we switch over to the types of structures, LED structures, like I discussed in the first slide itself. Based on these heterostructures, people have devices, surface emitting LEDs, edge emitting LEDs, superluminescent LEDs, and this mainly just to confine the light and guiding the light within the device, so that we have the maximum coupling to the outside media or the fiber. So in both types of LEDs, a combination of insulating material and junctions is used to guide the current flow to a small active region and guide the light produced out of the device into an easy position for coupling to a fiber. Surface emitting LEDs, which is called SLEDs, you can see the structure here on the right side, that you have at the bottom side, you can see this active region, a small region in a double heterostructure layer. You have a small active region, and right onto that we are coupling a fiber on top of this, so that the light which is produced out of this is coupled maximum to the fiber, because our fiber dia is around 6 to 8 micron core, or in case of a multimode it is around 62.5 micron. And then we have a confinement layers sandwiching these active layers. Then we have a silica insulation layer, metallization, heat sinks, and then we have a contacts metallization to provide the current or the voltage to make it forward bias, so that the active recombination takes place only in the active region. So this is one of the method wherein the light is emitted right on top of the surface of the active regions. Like we have seen in case homojunctions, the light is emitted from the edges of the active layer at the junction point. Here the light is produced at the junction, which is at the surface of the LEDs. That means I now couple this light maximum to the fiber. Here the data rate one can achieve is around 20 Mbps, and the light output is again having slightly larger aperture area, wherein I can couple this to the multimode fiber, and the coupling lens is used to couple this light maximum to the fiber. And this device is generated or developed by Burrus, a scientist, and that is also called as Burrus LED in honor of C.A. Burrus, who is the developer of this. So in SLED, the size of the primary active region is limited to 20 to 50 micron. The primary active region is just below the surface of the semiconductor substrate, which is perpendicular to the axis of the fiber. A well is etched into the substrate to allow direct coupling of the emitted light to the optical fiber. The etched well allows the optical fiber to come very close to the contact, and that so that the emitted light is maximum coupled to the fiber. The another area is edge emitting light LEDs, wherein rather than coupling right on the top of the surface of the active area, the light is coupled at the edges of this active region. You can see in the structure you have a double heterostructures. You have an active region which is running parallel to the axis of this semiconductor area, and then we have a metallization for electrical contacts, and then heat sinks, and then we have a two guiding layers to create a heterostructures, and this creates a stripe type contact geometry where the active layer where the recombination is taking place, and the light is now emitted at the edges of this semiconductor in a very confined manner, and the incoherent output beam, because the light is emitted in the form of a spontaneous emission, so it is incoherent, having slightly broad bandwidth, and that means I can now couple it to the multimode fiber much efficiently, and single multimode fiber as well as single mode fiber, because the spectral width is slightly reduced as well as it is narrow, and this is highly directional. So edge emitting LEDs have an advantage of transparent guiding layers with a very thin active layers of 50 to 100 micron. This reduces self-absorptions and narrowing the beam divergence. Light is emitted at one end face only. Couple more power to small numerical aperture fiber. That means I can couple this to single mode fiber. The higher data rates is achieved in case of edge emitting LEDs. Both fibers I can use in this. They have a smaller, narrower line width than as compared to SLEDs, and a high radiance. That means much larger output is achieved. Another area is superluminescent LEDs, wherein this is another form of edge LEDs. It has slightly higher power output, directional output beam, narrow spectral line width as compared to your EELEDs and SLEDs. One end is made optically lossy, that means it is totally reflecting. The another one is partly transmittive type, from where the light is emitted out. You can think of that this you have a cleaved faces on both the ends. One is mirror coated, the another one is slightly not mirror coated, so that the stimulated emission is not taking place here itself. The spontaneous emission is limited here, and the light output is maximum in this case, and the emission band is around 5 to 100 nanometer wide. That means I can now couple maximum light from this SLEDs, and this is based on a superluminescence phenomena. Now if I compare the SLEDs and EELEDs, and this you can see the SLEDs generate slightly 2 to 3 times more power than EELEDs. However, the SLEDs couple more power into large numerical aperture, that means multimode, whereas EELEDs, edge emitting, couples maximum power to the small numerical aperture, and ELEDs have a better modulation bandwidth. That means I can modulate much larger bandwidth as compared to SLEDs. If I just see the characteristics of LEDs, because I want to modulate this LEDs to couple it to the multimode fiber as a cheap solution for my modulation systems, you can see the light output as well as the forward current at the biasing which I am providing to this through a resistance. The forward current, which is now governed by the recombination of electrons and holes within the active region, shows a linear output as I increase the forward current versus the light output. That means now I can modulate linearly with this by changing the forward current or by modulating this light in the form of a sinusoidal or a digital signal to the form of a light output, which is also modulated in the same pattern form. You can see the output is slightly a parabolic shape it is having. The maximum coupling is within the 10 degree, plus minus 10 degree of LED output. How narrow I can make it, it is based on the structure, the homojunction or heterojunctions. As I move to heterojunction, it goes slightly lower, further lower. That means I can couple maximum power. The further parameters of this is full width, half maximum. What is the bandwidth of this LED output? The peak wavelength, the wavelength which I am mainly interested for propagation. The forward current it looks for. The rise time, the luminous intensity, that means the flux, and the LED radiation pattern, the parabolic shapes. These are the patterns or the specifications I must consider before selecting LEDs. If I see the LED power and efficiency, the internal quantum efficiency is around 50% for simple homojunction devices. That means the current which I am inputting to the semiconductor and the recombination which is taking place is the order of 50%, and that has increased to 60 to 80% in case of a double heterostructure semiconductor. The internal quantum efficiency is ratio of radiative recombination rate to the total recombination rate. That means the radiatively means how much photons are produced. The total recombination rate is how much total recombination is taking place, one in the form of a photon, another in the form of a heat energy. So that defines my quantum efficiency, which is related to your forward current. You see the last equation. Neta internal I by E, that means the forward current is also related to the quantum efficiency of this. So now this quantum efficiency is also related to the power output. As you see, the P intensity, the power output is related to quantum efficiency into h nu, which is related to the quantum efficiency I by E h nu. And in terms of wavelength, I can define nu as C by lambda. So that means the power output is now related to the wavelength output. You can see the, as well as the power is also related to the current feedback which I am providing to this. That means it is linearly proportional to this. I can increase the current, I can increase the power. Lambda now is a governing factor which says that the power on either side of the peak wavelength varies accordingly. So you can see the light output in case of a normal LEDs, in case of a ELEDs and SLEDs. The A and B figures downside shows the surface emitter. A shows the surface emitter output, which is slightly higher as compared to edge emitter. But edge emitter gives me the much narrower bandwidth.
Excuse me, sir.
Yeah. You have some question, sir?
Yeah, sir. In previous slides, sir, you have shown some lambda is there.
Yeah, lambda is there. I'll just cover in next slides how the output is varying is as compared to lambda, right?
Sir, lambda is wavelength or any other thing?
Wavelength, emitted wavelength.
Sir, for DC signal, there should not be any wavelength. This is emission wavelength.
You just see this the valence band, the conduction band. They are not discrete bands. They have some width. So the transition which is taking place is from the different bands within the conduction and the valence. So each of this transition produces a wavelength across the maximum peak wavelength, right? So there is a band available across the peak wavelength, which I will show in the next few slides, right, sir?
So, sir, the wave means the power emission is dependent on wavelength also.
Wavelength also.
So,
We'll see.
can we reduce this wavelength
Yeah, that will
by
reduce.
reducing the structure of the LED,
That's
size of?
what we have discussed. The wavelength confinement or the junction confinement is in a narrow structure, as well as when we switch over to laser, the wavelength is playing a much better role in case of laser. We want a single wavelength to be outputted to the fiber, right? So
Single.
we'll discuss all those in laser also, right?
Okay, sir. Thank you, sir.
Okay. So you see the temperature dependence of this output. In case of SLED, the output power is varying drastically. In case of SLED, the output power variation is slightly less as compared to ELEDs. That means because I want that when I am operating this LED for my modulation at the detector end, there should not be any variation on the light output which I am receiving at the detector point. If there is a variation because of one reason or the other at the laser itself, at the source itself, either because of temperature or because of current variation, it is going to affect at the detector point. So we want that the temperature variation should be minimum at the source itself. So you can see this parameter one must study, one must know that the temperature variation for which LED is important and which is minimum. So SLED is showing a minimum temperature variations, right? This curve is for a 1300 nanometer with a current forward current of 200 milliampere, and the temperature variation you can see from 20 degrees to 80 degrees, and the optical power is in the terms of milliwatt. So you can see the temperature dependence of the spectrum. You can see the light output in terms of wavelength as well as normalized light output. As the temperature increases, the pattern is broadening as well as the intensity is falling down, right? You can see the delta lambda on this side is related to the temperature and the wavelength also. The shift in the change in the peak wavelength is governed by these relations. So this temperature I must control while working on the source point of view when I want to modulate it, because any variation on the wavelength and any variation on the intensity is equally important from the detection point of view, which we will discussing in the next lecture in the 11 o'clock or 11:30, right? The spectral width, as you were mentioning, the spectral width defines what is the maximum wavelength which is available and what is the wavelength which is available around that. You can see in case of a surface emitting LEDs, the spectral wavelength is around 125 nanometer. So you have a one peak which is say 1.33, but around 1.33 you have another wavelengths are also emitted, because the conduction and the valence band, they are not discrete. They have some width, and when the recombination takes place, so this produces a slight band across the maximum peak, and this band leads to the modal dispersion, spectral dispersion, or spectral dispersion present in the fiber itself. So we want to reduce this type of characteristics of the source in terms of lasers or another mechanisms. You can see FWHM, or the full width half maximum, is around 1.6 times for the SLED than to the ELEDs, and it is further narrowed to 30 nanometer in case of a superluminescent operation. You might have seen during Deepavali the so many LEDs which is available, and they are very bright LEDs. So they are part of superluminescent LEDs. The pattern broaden with increasing wavelength and are wider for surface emitters. So if I just take use of a simple LED driving circuit, you can see the left hand side, you have a transistor, you have a which is having a LED or light emitting diode at the collector point, and then the analog output analog input which I want to modulate this LED output. So you can see when I modulate this, when I put the biasing voltage across the input, analog input at the base of the transistor, the current which is flowing from the collector to the emitter is varying as per the base voltage. So whatever communication, whether it is analog or digital, I can modulate the current of the light or LED. When I modulate the current of the LED, that means the current is now related to your power output. The power output of the LED is also modulated. So the another area, another on the right hand side is a linearized low frequency operation, wherein the analog input is put into the positive or the non-inverting input of the op-amp, and with a feedback circuit with a emitter coupled to that, it produces the light output. A simple mechanism wherein this LED can be made to operate, but a complex system one can think of that I want this LED output, the Q point of the operation must be at a fixed value, at a fixed output, and the temperature fluctuation should be avoided. That means I must have a thermistor control or thermoelectrical type of control of the temperature, as well as a feedback mechanism wherein the light output can be coupled to the detector, so that I can maintain a feedback mechanism to control the Q point of operation of my system. So we will discuss all that in the case of a laser. So advantage of LEDs, they are easier fabrication, lower cost, simple driving circuit, lower temperature dependence, better linearity, more reliability. Now I'll switch over to the laser diode. As we know, the disadvantage in case of LED is it has a slightly broader spectral width. That means around 40-50 nanometer is available to me, and the light output is also is not enough that I can transmit for 10 kilometers or 20 kilometers of this. So the laser diode has come into the picture. The LEDs is based on spontaneous emission. The laser diode is mainly light amplification by stimulated emission of radiation, wherein we have a coherent light, narrow beam width. That means I have a very small angular aperture of light which is available to me, and this produce a power output of 20 milliwatts or so. And because the laser is coherent, so I can couple maximum power of 20 milliwatts into the fiber, which is around 50 to 80%. And we will discuss all these coupling issues in this few slides later on. You see, in the semiconductor or in otherwise also, there are three processes which appears. One is absorption. When I input some energy to the electrons you can see in the left hand diagram, at the ground state E0 jumps to the higher energy state, which is E1, by absorbing the photon of energy h nu is equal to E1 minus E0, and it reaches to the higher energy state. I call it as a absorption of the photon, and that excite the electron to the higher energy state. Now this electron, after certain time, based on the time response of the higher conduction band, it drops back to the lower energy state. When it drops back, it emits energy in the form of a photon, which is h nu is equal to E1 minus E0, and that is called spontaneous emission, and it is random, right? Now think of a situation wherein you have a electron which is available at the higher energy state, and now you have another photon which is having the same energy or as equivalent to the band gap of the E1 minus E0, is interacting with this electron. So what happens? This interaction creates two photons. The one photon which is already moving from the left side to the right side, another one when during the interaction at the higher energy state, when this electron jumps back to the lower energy state, releases the photon. So now one photon creates two photons. So that is called stimulated emission, wherein the energy of the photon which is interacting with the spectral band of the conduction and the valence band of the semiconductor is creating two photons, or there is a coherent release of energy of one particular wavelength, which is equivalent to the band gap energy of this semiconductor, which is E1 minus E0. Now think of a situation that within this process, if I put this structure in two mirrors, one mirror on the left side, one mirror on the right side, now this photon keeps on oscillating back and forth. And if I somehow make the number of electrons at the higher energy state much larger, then they interact in a stimulated fashion and then creates much larger output. So you can see here, now I have the first picture on the left hand side shows that you have a excited state atoms or electrons. They are randomly releasing their photons when they de-excite back to the lower energy state. Some of them are in coherent state, some of them are incoherent state. Now I put that in the form of two mirrors. Now only those photons which are oscillating within the two mirrors, they are interacting with the higher energy electrons and produces a coherent output which is equivalent to the band gap energy of the valence and the conduction band, and creates a photon which is having energy of that particular band gap energy or a particular wavelength. So that simple operation leads to a stimulated emission which overpowers the absorption and the spontaneous emission in the semiconductor. So the two conditions which needs to be satisfied for stimulated emission to overwhelm the spontaneous emission are: the population of excited level should be greater than that at the lower energy level, and the radiation density in the medium should be very large. That means I must have electrons at the higher energy state much larger, or I call that as a population inversion, wherein I make these electrons or atoms at the higher energy state much larger. That means you can see on the right hand side top figure, you have number of electrons at the higher energy state, which is population density is N2. If they are higher, and this photons on the left side, when they interact with this, it produces a coherent output with a particular energy or wavelength which is governed by the band gap. So we need that N2, the population density at N2 must be larger than N1 for this laser output or stimulated emission to take place. And this phenomena is called pumping. So one is electrical pumping, wherein the electrical current pumps these electrons or atoms from ground state to the higher state and produces the more population inversion in the semiconductor. So stimulated emission photons will have identical energy because the band gap is confined, identical wavelength that produces an identical wavelength, narrow line width because the other wavelengths are now suppressed because of spontaneous emission is overpowered by the stimulated emission. You have an identical direction because we are now passing this light in a very narrow beam width. Identical phase, they are coherent, and because the phase is matched, and they have the polarization. That means the laser output, you can see it has a coherent, it has a narrow beam. You can see the laser pointer which is available in the market. When you light this, shine this to the wall, you can see the spot is perfectly circular or available at a longer distance, whereas if you shine this LED to a longer distance, you won't get it because the coherence is there. Narrow beam is there, the energy is confined in that wavelength or narrow region only, right? So these are the advantage of the laser. So this advantage is being made use for the laser in fiber communication system. So now a slight basic physics. You have now on the right side, left hand side of the figure, you see that you have a light inputs which is oscillating between two mirrors, which is M1 and M2, right? So one beam goes from one mirror to the another and gets reflected, right? So now different wavelengths, which is if they are available within these two mirrors, they interact and they superpose the interference between the incident beam to the reflected beam from the mirror M2 and produces a standing wave. Or only those beams, only those modes which are constructively interfere between these two mirrors having a separation of length L is sustained in this cavity, right? So you can see a mode which M is equal to 1 which is having only one wavelength equivalent to your length of the spacing of the mirrors, or m is equal to 2, which is half of that length of the mirror, and m is equal to 8, which is 1/4 of the length of the mirror. So these modes, they exist between these two mirrors. So based on this pattern, you can plot a radiation intensity pattern versus the wavelength, and in terms of the reflectivity of the mirror, if you have a sharp reflectivity, r is equal to 0.8 or r is equal to 0.4, the width of the spectral output, if M2 is partly reflecting, then you can see a part of the light output is available to me, and the bandwidth or the light output available to at the partly reflecting M2 output is governed by the reflectivity of the mirror M2, and it gets broadened if I make it much sharper, 99% reflecting type, it becomes much sharper. So that means I now select only one particular wavelength or a very narrow bandwidth of the laser using these techniques, right? So you can see the resonant modes which is available within this Fabry-Perot resonator. This phenomena is called Fabry-Perot resonator, is governed by KL is equal to m pi, where m is 1, 2, 3, 4 integer, and L is the spacing between the two mirrors, and K is the optical wave number. So this is the basic principle of the laser structure to work as a coherent output or narrow beam structure. And now in case of a semiconductor, again the phenomena of homojunction and heterojunction and double heterojunction comes into play with this area. You can see the downside right hand side picture. You have a p-type gallium arsenide, you have a n-type gallium arsenide. Now it is a homojunction. You have a active region which is sandwiched between these two barrier layer, and now you have a ohmic contacts or the metallization contacts. The two surfaces at the left and the right hand side, they are clear mirrors. They are polished. The semiconductor is polished so that they act like a mirror. Now the light output or the spontaneous emission which is taking place in the active region is now governed by the mirror or Fabry-Perot resonator cavity between these two mirrors. So they keep on oscillating. So only those modes which is governed by the length of this active region or between these two cleaved mirrors is sustained in that. You can see one of the reflectivity is 0.99 on the top side, another reflectivity is 0.90. That means whatever the laser is available in the market, only 10% or 1% of the light output is available to us, and that too is much higher as compared to what is available inside the cavity itself, inside the semiconductor. So in case of a homojunction material, you see the current density, the required current density to create a population inversion is of the order of 10⁻⁴ ampere per centimeter square, and that is slightly inefficient. I need to pump more current to get a small output or a small power output from this. So the people devices a semiconductor which is double heterojunction, so that this current density or a small current requirement suffice my requirement of population inversion in that. So going back to the Fabry-Perot laser cavity, again you have a SLED type of operation or EELED type of operation in that system. So you have again two confinement here. You have the active layer which is around 0.1 to 0.2 micron size only. The lateral size of the semiconductor is around 5 to 15 micron, and the longitudinal size is around 250 to 500 micron only. So that much amount of semiconductor is being made use of to produce this light output, which is the pattern of this light output. You can see which is around 5 to 10 degree in the azimuthal case, and in the longitudinal case it is around a larger area, a larger angle, which is around 30 to 50 degree azimuthal angle. And now the requirement is again how we can confine this angle so that I can couple maximum light to the fiber, and that too much more coherent and much light output to be available to me. You can see that the active region is only 0.1 and 0.2. That is what the fabrication challenges are. So the laser output, if you see the pattern, they are of this shape. if I see the pattern, if I divide this, the Gaussian profile of this laser output, you can say within this Gaussian output there are discrete longitudinal modes available to within the laser. I can select one of them through interference pattern. So if I switch over to this laser spectral width, which is maximum required for my communication, so you can see the LED spectrum is of the order of 30 to 50 nanometer wide. Multi-mode operation is possible. The standard laser output is around 1 to 3 nanometer, which is I can make couple this to the single mode fiber. And now recently the single frequency laser on the single wavelength with a spectral width of 40 picometer is available. So we'll switch over to this, how we can devise my semiconductor so that I can get only a very narrow spectral line, so that my modal or spectral dispersion within the fiber is minimized, right? So again, the heterojunction I discussed in the LED case, double heterojunction is strip geometry type of fabrication takes place, wherein the current density or the amount of power which I input to the metal contacts of the laser is reduced slightly in that case. So you can see the double heterostructure is, again you have a N-type aluminum gallium arsenide, a P-type gallium arsenide. With a P-type gallium arsenide active region, you have a confinement layer and the active layer where the recombination takes place. And now within this active region, I can create an active strip geometry so that the output is available to me in the only confined area, right? So this is a strip geometry. You can see the in the diagram itself. Strip of that is mirrored, totally mirrored. So the light is available on the edges of that. Again, the structure of edge emitting or surface emitting is also created in this laser also. So you have again the refractive index profile, wherein the light is confined within the active region, because the sides of this active region is having slightly lower refractive index as compared to the active region, and that is generated because of the proton bombardment of oxide or silica. This step therefore acts as a guiding mechanism which overcomes the major problems of the broad area active devices. Now again, as I said, I want my output to be very narrow, right? Because I want my spectral width to be very narrow. Still I have not devised anything. It is just in a region strip geometry. In the previous slide, what people have done while fabricating this active layer, they have created one grating onto that active layer. You can see on the left hand side top, right onto the active medium or active layer, people have created a grating, and the grating pattern is being etched onto the active medium. Now this grating pattern, rather than the fabric pericavity layer where the two mirrors are governing the light output, here the grating pattern governs which wavelength will be outputted, right? So the wavelength which is output, lambda b, is governed by twice Ne lambda delta, which is the pitch of the grating, and k the propagation constant. That means now the refractive index of this material and the pitch of the grating defines what is the wavelength is emitted out of that, because only that wavelength which suffices this structure is available to me. So this is what is called distributed feedback laser, which is called DFB laser. And you can see here, can I show?
Yes.
You can see this is DFB laser. This is DFB laser. It has a number of pins onto this. I'll be explaining all those pins, and this is now coupled. The output of this is coupled with a fiber, right? Another end of this fiber is connected to the connector. Now I can connect this connector to the another fiber It can be 1 kilometer, it can be 10 kilometer. I can supply this laser output to the outside media through this uh, structure, which is called DFB structures. I'll be discussing this. I am using right now this type of lasers, which is very high power. It is 10 milliwatt laser operating at 30 milliampere of current, right, within 5 volts of operation. So a low voltage, low current operation is possible using DFB lasers. I'll be discussing on all those things. Okay, sir. So a distributed feedback laser is a type of laser diode where the active region of the device is periodically structured as a diffraction grating. You might notice the PN junction laser or LED is just a 2-pin device, right? A P-type material and an N-type material, an anode and a cathode. But this DFB laser has number of pins. As I discussed, that I want my lasing output to be Q point of that should be maintained at a constant point value. That means I must have a feedback mechanism of the tech or thermistor and the thermoelectric cooler and the photodiode, so that I maintain that Q point of my operation. So all those pins corresponds to, in that DFB laser, corresponds to that points. I will be discussing all those, how to control those areas, all those parameters in this. The structure builds a one-dimensional interference grating, which is called Bragg scattering. Bragg is a scientist. This lambda b, the wavelength which is produced, is based on the Bragg wavelength, and the grating provides optical feedback to the laser. DFB lasers diodes do not use two discrete mirrors to form the optical cavity. Rather, they act as the grating acts as a wavelength selective element. You can see the refractive index NE, or the pitch of the grating, defines which wavelength. That means which wavelength is outputted. That means I now control the wavelength of this laser, which is outputted to the system, by just varying the refractive index or the pitch of the gratings. So varying the refractive index is possible using the current, injection current variation. So that means now this laser becomes tunable wavelength. Many times we studied that wavelength of the laser is only fixed. It is not so. I can tune this laser. The DFB laser which I have just shown, I can tune that laser wavelength to a particular region, say 10 nanometer or so. I can tune by modulating it, by changing the Q point of that laser point of operation. That means the different wavelengths I can I can make use of to be outputted. And this is what is called tunable DFB lasers, right? So this is in contrast to the Fabry-Perot laser, where the mirrors are used. Temperature dependence of the oscillation of the wavelength of DFB laser is determined by the temperature dependence of the refractive index of the material, which is around 0.1 nanometer per degree centigrade. That means if 1 degree temperature is varied, the wavelength is changed by 0.1 nanometer. That means the wavelength output, if I want to control, I want to control my temperature as well, right? So a change in refractive index alters the wavelength selection of the grating structure, and thus the wavelength of the laser output produces a tunable diode laser. DFBs are anti-reflection coated on one side, which is anti-reflection, and highly reflective on the another sides. In this case, the grating forms the distributed mirror on the anti-reflection coated side, while the semiconductor facet on the high reflected side forms the other mirror. These lasers generally have higher output power, since the light is taken from the air side, and the HR side prevents power being lost from the back side. Another area is DBR laser, where the grating is fabricated outside the active region. Now the light which is coupled is from the outside grating region. That means the light which is taking place from the active region passes to the grating, is reflected back to the active media, and that oscillates back and forth in the active medium. Or another architecture may be that I have a grating outside the media, and now I rotate this grating. You might have heard the grating equation, where, or monochromator equation, where by rotating the grating, the wavelength which is passed on to the active media can be tuned. That means the wavelength which is made to be available to the laser radiation output, I can tune by changing the grating wavelength or grating angle of that. So this is what is called DBR, or distributed Bragg reflector laser. So as I said, the thermal properties of DAB lasers, you can see on the right side, the wavelength is varying from 1.565 micron to around 1.570 micron, right? Around 15 picometer, 15 nanometer variation of the wavelength one can achieve by just tuning the temperature of the junction. So by varying the temperature from 20 degree to 108 degrees centigrade, I can tune the wavelength of my operation, right? But at the same time, the light output also falls. You can see on the left hand curve, the light output at different temperatures, they are changing. So I must control through feedback the light output as well as the temperature for my operation. So now I switch over to the quantum well lasers. Basic idea is again how fine tuned I my laser, so that I can get only a very confined light output in terms of wavelength, right? So we know that if the dimension of the waveguide is, if I restrict it to of the order of wavelength, then the photons which is moving inside the cavity, cannot behave like a wave, but it behaves like a quanta or particles. So if I now fabricate my active region to be just 5 to 10 micron, and the width is around 10 nanometer, which is of the order of the wavelength which I want to make use it, and now this confinement of the waveguide defines the active region, or the population inversion is taking place within the conduction and the inversion valence band of that media. Only that wavelength is outputted through that active region. So most semiconductor lasers are very thin, which is around 20 micron or so, but here it is 5 to 10 micron and 10 micron as a width. So in the vertical direction, but this is not thin enough to cause quantum behavior. In quantum wave well laser, the cavity height is reduced to around 10 to 20 nanometer, and the cavity width is around 5 to 10 micron. So this amount of material in the active region, which is very small, reduces the current input to the quantum well lasers, and because the amount of active region is reduced now here. So lower lasing threshold is achieved here. So quantum well lasers have a much reduced sensitivity to temperature change compared to DBR and DAB structures. They have a much narrower line width. That means I can have a much sharper wavelength available to me. And the width of the active region is much smaller as compared to DAB or DBR lasers. Lasers with a single active region are called single quantum well lasers. I can stack them together, so create a multiple quantum well lasers or structures. So that gives me much better output in terms of the intensity. So by applying multi-quantum well structures to the active region of the laser, the performance of the laser, such as threshold current, temperature characteristics, and modulation frequency, were significantly improved over DBR and DAB structures. However, the disadvantage in case of MQW as compared to SQW is that they are slightly broader as compared to SQW single quantum well lasers, but it's still narrower enough as compared to DBR and DAB structures. So again, after that quantum well lasers, the another dimension which has come is vertical cavity surface emitting lasers. Here you have a stack of DBR on the right side. Downside, you see the diagram. You have a DBR, distributed Bragg reflector, which is around 20 to 40 layers. On the P-type materials, you have N-type materials. So you have active region which is now sandwiched between the such P and N structure with a distributed Bragg reflectors. So the active region now emits output only in the vertical direction. As I said in earlier case also, the vertical cavity gives me the maximum coupling, because I can couple directly the fiber onto this. The left side picture shows the details of that. You have a very small region of conductive region or active region, and then we have a at the top surface the light output, which is available to me. So multi-layer stacks must have a reflectivity as high as 99.8%, and the layer thickness must be precisely controlled to ensure that the laser resonator frequency falls within the gain bandwidth of the quantum well. So this has a lower threshold, which is around 5 milliampere. I can operate such a structure by 5 milliampere of operations. Low divergence, nearly circular beam pattern, well suited to the optical fibers. Right. This is the another area which is now currently available for fiber optic communications. So VCSEL, instead of emitting from the edges, it emits from the surface. It is constructed by laying down a large number of thin layers of semiconductor materials. The device emits light vertically through the stack of material layers. The mirrors are made of alternating layers of materials of different refractive indices with controlled thickness. The stack forms a Bragg grating, which is a wavelength selective mirror. The laser is so confined that it forms a quantum well in which light behaves as induced photons rather than as a wave or rays. Typical dimensions around 12 micron in diameter, and for single mode operation, and 20 micron for multi-mode operations. So there are two wavelengths which is currently available. The research is going on that direction, 980 nanometer or 850 nanometer, and that is operation is up to 2.5 gigahertz is possible with such single mode lasers of VCSEL. So that means I can modulate my input signal or modulation frequency of 2.4 gigahertz is possible with a current of 5 milliampere with a light output is much higher as compared to this. Another area is in-fiber lasers. You see erbium doped fiber. The fiber, while fabrication, erbium is a material which is when doped in the fiber, it becomes slightly special as compared to the normal fiber. And when I sandwich this fiber into two fiber Bragg gratings, now as I said, the fiber Bragg gratings or FBR is having a particular grating structure wherein the Bragg wavelength which is reflected back is governed by the pitch of the grating structure. That means one fiber and another fiber on the right side, I can select my wavelength by changing the pitch of these structures. We at the CSIO is having this type of facility wherein we can create this fiber Bragg gratings in our labs. And now if I sandwich EDFA or erbium doped fiber between the two fiber Bragg gratings, that means now the wavelength which is now oscillating between EDF fiber is now controlled by the two fiber gratings, right? So that is the mechanism where the mirrors, two mirrors are now replaced by two FPGs, right? So this is what is called in-fiber laser. The fiber itself now acts like a laser. So the transition which is taking place in the erbium doped fiber is now governing by the two fiber Bragg wavelengths, which controls the light output onto the right side. So a fiber laser is constructed from two FPGs which acts as a wavelength selective mirror and a length of EDFA fiber as a gain select section or a cavity. The laser is pumped with a wavelength of say 980 or 1480 nanometer for erbium, where is the excitation level for erbium appropriate to the lasing. When you supply 980 nanometer or 1480 nanometer wavelength to the EDFA fiber, it gets, the erbium gets excited to higher energy state, but when it transits back to the lower state, it emits a particular wavelength. Now that particular wavelength we are controlling by the two FPGs, right? So this is the basic of in-fiber lasers, right? So EDF fiber, you can see you will be having a lecture on this by one of my colleague, Dr. Umesh Tiwari, during afternoon from 2 to 4 on EDF itself. So you can see you have a EDF fiber which is erbium doped fiber where the fiber is doped with the erbium element. Now if you pump this fiber with a laser of 0.98 micron or 1.48 micron, so the erbium is excited to higher energy state, but when it relaxes back, it produces a wavelength which is now is amplified to the level of the two relaxation or stimulated emission value of the EDF fiber to the output. That means right now if I want within the fiber itself to amplify my optical signal, think of a situation that I am transmitting my signal from laser to 10 kilometers or 100 kilometers of fiber. Due to material losses or all those things, the light output gets attenuated. So I can use this EDF fiber there itself. I can splice this EDF fiber or EDF amplifier in the output of the fiber, and now I can amplify those signals. You can see on the left side the optical signal which is inputted to the EDF, the output of that is again amplified. That means it acts as a repeater. The fiber itself now acts as a repeater. I can amplify my signals to a longer region using EDF fiber. So you'll have more details in the afternoon section through one of my colleagues who will be delivering this lecture. So another area is fiber ring lasers, wherein a fiber, this type of structure of EDF and the tunable fiber Fabry-Perot filter is now looped in the form of a fiber. You now pump this input light to this structure, the coupler or the ring, and now EDF and the tunable fiber controls the stimulated emission of one particular wavelength, and the part of this output is available to me. So this is what a fiber ring laser is, and now I can have a tunable wavelength of the laser. Here I am now avoiding the semiconductor. Here the EDF now acts like a laser to me. So here, because I am not using any control of current, because only light is now propagating around the circle of the ring. So this is what the wavelength is available to me in the form of optical. Now I must now, if I want to modulate that, that means I must now modulate externally this light output so that my modulation of the light amplitude or phase or frequency of that is possible using in this mechanism. Now dependence of coupled power to optical fiber. You can see that we have discussed the angles over which the light is emitted, the size of the source for the case of LED versus laser, the fiber core size and the output pattern of these LEDs and lasers, the alignment of the source and the fiber, the coupling characteristics of the fiber such as numerical aperture, refractive index profile, the typical radiation pattern which is around 10 to 15 degree in case of LEDs, and in case of LED laser it is around 4 to 5 degrees, and how much it is spread. So all these parameters one must study before couple this to the fiber. So one is the fabrication of this laser or LED, another domain is the how to couple this light to the outside media or to the fiber or to make it use of the user. So besides fabrication, the fabrication of this structure, the coupling of light to the laser structure or LED structure is the most tedious or most costlier part as compared to the laser or LED fabrications. You can see this, the active region refractive index is around 3.5, whereas the refractive index of the core is around 1.5. So that means if I want to couple the high refractive index to the low refractive index media or the fiber, there must be some losses. And that means I must now devise my mechanism. So there are 4 mechanisms which exist as on date. One is the green lens, which is a gradient index refractive index lens, where in the active region you have a one lens, green lens, and then you are coupling this output of the active media to the fiber. You can see the surface emitting type of laser is much more advantageous as compared to edge emitting, because the coupling becomes more easier. Another domain is the ball lens type of structure. Again, these lenses, all those things, they go into a micron dimensions because the active region is only of the order of 1 to 5 micron only. Another area is the direct coupling. That means I now put my fiber directly right onto the top of the active region, so I can couple the light to this. Again, all these 3 are inefficient. Another is within the fiber itself, can I now create a lens on it fiber. So that is possible. I can etch the fiber end so as to create a lens onto that, so that I can couple the maximum output of that. So in maximum of the cases, I must use a refractive index solution, which must now confirm that the light output coupling from the higher refractive index to the lower refractive index is the maximum, right? So this type of techniques are being used in this maximum light coupling output. So again, I must consider the laser characteristics before finalizing which laser I must take. Again, FWHM, that the output of the laser, what are the wavelengths which is available to me, the maximum peak wavelength, which wavelength I want to work, 800, 900 or 1300 or 1550, threshold current, what is the maximum value I can operate on that, or the operating current which I Q point of that operating point I must consider, the rise time of the laser or LEDs, output power what I must couple, I must find out what are the losses which is available in the optical fiber or the detector point of view. I must consider before deciding my Q point and the output point of the output of the laser or the operating temperature. You can see the threshold current is below the threshold current you have a spontaneous emission, above the threshold current you have a stimulated emission which overpowers the spontaneous emission, and there is a variation of temperature versus the light output and the current output also, right? And then I must discuss the modulation of the lasers. It can be either directly by varying the injection current of the LED, because it's a LED, so because it's a PN junction, so I can directly control the forward current of the PN junction by modulating it through a analog or a digital signal, or externally, which I will discuss now. So this is how I can modulate the current of the laser, and parallelly you are modulating the light output of the laser, either sinusoidally or digitally. So I can superimpose onto the Q point of that both analog as well as digital signal. So the current input to the laser is converted into the modulated signal, modulated light output signal of the laser. Another area is external modulation. That means I have a light which is available from the laser diode, like in case of a in-fibre laser where the current is not there, only light output is there. So I use EOM, which is external optical modulation, wherein the phase or the amplitude or the frequency of the material I can change, or the light output of the laser I can change, and then it is passed on to the fiber link, and it can use go up to the 60 gigahertz or so. So this is how the external optical modulation takes place. You have a one structure which is based on the lithium niobate crystal. You can see there are two arms. One of the arm is now modulated with a RF signal or a signal which I want to communicate to the outside media. You have a laser output, which is light input in the top side of the diagram, and then it is now divided into two parts, and it is now passed on to the at the junction point, which is a combiner, right? So based on the input which I am supplying to the one arm of the interference pattern of this, the shift of phase or wavelength or amplitude, I can control this. You can see in the downside, the light input is now interfering either constructively or destructively. Downside, you can see when it is constructive you have a maximum output, when it is destructive you have a lesser output. So by controlling the RF or the input signal, I can modulate the light output which is coming out of the this structure, which is called Mach-Zehnder interferometer or MZM, which uses a sort of a new material called lithium niobate, and the phenomena is called electro-optical modulation, electro-optic modulation, wherein I am modulating the parameters of this crystal or refractive index of this crystal to modulate, to get my modulated input signal, right? the phase shift delta theta is around 180 degree into V in by V pi. V pi is the voltage which is required to modulate my signal to get 180 degree phase shift of the input signals. V in is the my modulated signal, right? So this is what I am now developing at my institute. This DFB laser you have seen, you see on the top you have a laser operation circuit, and now I must now drive this laser by a bias control. Parallelly, I must have a temperature control using a tech which is called thermoelectric controller. I have a photodiode. You can see on the right side you have a laser diode LED which is coupling my output to the fiber, to the outside media. A part of this laser diode output is also sandwiched. A part of this is also outputted to the photodiode which is fabricated inside this DFB structure to monitor the output of the laser. If there is a degradation in the laser diode output, I can control using this photodiode which is fabricated in this structure. Using this, I can modulate my Q point. I can increase or decrease my Q point of the laser diode by making it constant. Same way, if there is a temperature fluctuations of the junction of the laser diode because of the current, I can use a thermistor right onto the junction itself to measure the temperature of that, and then a tech cooler, thermoelectric cooler, through Peltier effect, I can pass on the current to this to create the temperature control. That means I can increase or decrease the control of the temperature. Now I can modulate this Q point of the laser using data clock or data by data conversion unit. All these inputs are going to the laser diode. So you can see the complexity. The simple laser, which is a 2-pin diode, a PN junction, has now switched over to the 14-pin configuration, having all those features in that. Right? So this is what commercial DFB laser is available, which I have just shown. You have a power output which is 10 to 30 milliwatt. The threshold current is around 25 to 60 milliampere. The wavelength range is around 1540 to 1570 nanometer. And you have a tech current which is 1.2 ampere. That means I can pass into it 1.2 ampere of current to control its temperature. You have a thermistor whose resistance changes from 9.5 to 10.5 kilo ohm based on the temperature, and the operating temperature range is -20 to 65 degrees centigrades, right? So I can control my Q point, the wavelength region, the temperature control, and the grating pitch. All those features I can control using this. So these are the components: DFB diode, thermoelectric cooler, thermistor, photodiode, optical isolator, and fiber coupled lens. All these features are now fabricated on one device, and this cost is around 1.5 lakhs. Right? This is what the comparison between LED and laser diode is. I think I have discussed most of this: low efficiency, high efficiency laser diodes, slow response time, fast response times, incoherent coherency, higher bit rates, less distortion, longer communication distances, lower dispersion, lifetime is of the order of 10 raised to power 7 hours. So with this, I thank all of you for your hearing me. If you have any questions or any discussion you want to have, I am willing to have. Yes, please.
मैं तो नो क्वेश्चन बोल रहा था यार.
हाँ सर बोलिए. है?
Balaji, sir, do you have any
question? No.
Hello.
Yes, sir. Yes, sir. Maybe. Huh?
No question, sir.
no questions?
Close.
ब्रेक ले लेते हैं. ब्रेक ले लेते हैं.
हाँ.
Any query from any of the center? They can ask. So if there are no queries, then we'll have a tea break of how many minutes? 20 minutes, and we'll reassemble again at 20 minutes after 20 minutes.
Okay. किधर है? उससे
कैंटीन से उस साइड
जो हॉस्टल सा दिख रहा है सामने. चलिए. इस पे माउस नहीं चलता है. अच्छा, इससे
Yes,
हो गया.
yes,
All around. Huh? Okay. Once again, welcome. The next topic is photo detectors for fiber optic communication. As we discussed in the morning, that the light or the wavelength or the amplitude or the intensity which is available at the receiving point, the first interface goes with the photodetector, the light which it needs to be sensed. As I said, the light is now comprising of a particular wavelength or the amplitude or its phase. So this first interface or photodetector, which is light sensitive, is the first block diagram in any receiving circuit for this. So this photodetectors not only in communication, but it has a application in the area of medical, automobile industry, safety and analytical instruments, cameras, CCD cameras, and your mobile phone, astronomy, industry, and the various type of photodiodes which is now currently available in the market is a photodiode, pin photodiode, avalanche photodiode, photomultiplier tubes, microchannel plate, image intensifier, and charge coupled device. So we'll go one by one on that and see how I can build my setup, what precautions I must consider to handle these photodiodes for detection of or replication of my input signals. So the photodetector requirements for performance is high sensitivity at the operating wavelength of the source. That means once the wavelength of the source is defined, then my photodiode material characteristics should be such that I must know that the two must mesh together. Short response time to obtain the desirable bandwidth, minimum noise contribution, compatible size for efficient coupling and packaging, linear response over a wide range of light intensity, stability of performance characteristics, low bias voltage, and low cost. So these are the requirements, prime requirements for selection of photodetectors. Now if I go for the mechanism, how the light is sensed by the detector. So photodetector converts light into electrical signal, which I call it as a photocurrent. So a photon is creating an electron hole pair, and this electron is now made available at the outside media, outside resistance in the form of a current, and then producing a photovoltage. So there are two distinct photodetection mechanisms. One is for external photoelectric effect, which is being used in photomultiplier tubes. Another area is internal photoelectric effect, where PN junction photodiodes, pin photodiodes, avalanche photodiodes, they are finding applications. So let me first explain to you what photoelectric effect is. You might have read during your elementary classes that when an incident photon hits an atom, if its energy is much more than to the binding energy of the electron, this electron gets revelated outside the atom. So that is what is called a photoelectron. Only thing is the energy of the photon must be greater than the binding energy of the electron. So that is the basic principle of photoelectric effect. So that means if I have a photon, if I make use of some material wherein I can eject electrons out of this material, I can sense how many photons, which wavelength it is having. So an incident stream of photon strikes the surface of a material having low work function. If the energy of photon is higher than the binding energy of electron, then this electron will be freed from the material surface by absorption of the incident photon energy. A minimum amount of energy is required to liberate a single electron from the material is called work function and denoted by phi. The ejected electrons is known as photoelectrons. This mechanism is used in photomultiplier tubes. Let me now explain to you what photomultiplier tube is. So what it should have? It should have one, a cathode, which I call it as a photocathode, made up of a material which wherein the photon is, if it is made to fall onto that material, it liberates electrons. Now I must have some mechanism wherein these electrons, the photoelectrons, I must collect it at the anode point. In between that, I may look for a multiplication of electrons using secondary emission process. So if you see on the right side, you have a photocathode, which is a photosensitive material. The photon hits this photocathode, ejects the electrons out of it. Then there are number of diodes. You see the red colors structures. They are called diodes. And now between the photocathode and the anode, I have supplied 1000 volts voltage across it, and that 1000 volt I have subdivided into these diodes, say 10 numbers of these diodes equally. Say 100 volt is available to me between cathode and to the first diode, 200 volt between the first between the cathode and the second diodes. Like that, the structure you can see on the right side. So once the photoelectron is emitted from the photocathode, it is driven towards the photo diodes. Now because you have a high voltage appearing across it between the photocathode and the diode, so it takes the enough kinetic energy and hits the diode structure. So this diode structure creates multiple electrons based on the secondary emission, because it has a high energy. The electron is having high energy. Now these electrons keeps on multiplying further and further to the last diodes, and then one photon, which is creating one electron, gives me somewhere around 10 raised to power 4 or 10 raised to power 6 electrons at the output. So this is how the photomultiplier tubes works on. So the photocathode of silver, oxygen, cesium, antimony, cesium, silver, bismuth, oxygen, cesium, having low work function is being used. The electrons hitting the diodes have a high kinetic energy due to established high electric field. The electron gives up this kinetic energy, causing the release of electrons from the diodes. This process is called secondary emission. The incident electron at diode can liberate more than one secondary electrons, thus amplifying the detected output. So this is how the structure is. So this now is, there are two types of structure available. One is side-on PMT, another one is head-on PMT. You see, this is head-on PMT, this is side-on PMT, and this is the photocathode. These are the diodes, number of structures, and you have number of photoelectrons or electrons which is available to me. And you have now between this to this a high voltage appearing across it. At the end of this, you have a final output, a final current output in the form of electric current based on one photon. So this is how it is sensitive it is. That means one photon is creating around 10 raised to power 4 or 10 raised to power 6 electrons out of it. So this is how the current to voltage conversion for PMT goes. You have this cathode, photocathode. One photon is creating one electron. Then you have so many diodes, and each of these diodes is now potentially divided as compared to the photocathode to the anode. And the final current which is available to me is passed on to the resistance, and this voltage which is produced is now passed on to the op amps to get me the output. Now this I can go for further onto the multi amplification system. So this is how it works. So the PMT characteristics, if I want to make use of this, they are photocathodes of these materials, silver, oxygen, cesium, antimony, cesium, diodes made of either nickel or stainless steel with copper and beryllium alloy, coated with beryllium oxide, magnesium oxide, gallium arsenide phosphide, so that I get the secondary emission. And the electron multiplication of the order of 10 108 times is possible. That means one photon creating one electron at the photocathode is multiplied by 10 or 108 times at the dynode structures. Now this multiplication keeps on rolling further and further to the n dinodes, and finally what we get, a 10 raised power n times magnification of that. So again I must consider quantum efficiency, which is the ratio of photoelectrons emitted from cathode to the number of incident photons. Not all photoelectrons are available to me at the output end. Some may be getting trajectoried to different area. Electron transit time, electron collection efficiency, spectral response characteristics, gain, linearity, drift, hysteresis, dark current. These are the features, these are the characteristics of PMT which I must consider, right? Output variation due to high voltage supply ripple, temperature stability, load regulation, magnetic interference, because the electrons is trajectorying from one end to the another. Any magnetic interference cause a change in the trajectory. That means there will be a loss of electric output. So this is how PMT looks like, and there is a socket which gives me signal output, signal ground, power supply ground, high voltage ground, and the divider circuit for diodes. This is how the response looks like for different materials. Like you see, for multi-alkali elements, the response is like this, and for bi-alkali element photocathode, the response is this. For silver, oxygen, cesium, the response is this. So it varies from one end to the another. This is for 900 to 1700 nanometer region for fiber optic communications. This is NIR PMT from Hamamatsu, Japan, having photocathode material of indium phosphide and indium gallium arsenide, and you can see the quantum efficiency and the cathode radiant sensitivity is governing by this curves. So that gives me output, the spectral response. If a wavelength, if a different wavelength are falling onto this photocathode, it generates different current output. And this typical gain based on the PMT supply is linearly varying from 10 raised power 4 to 10 raised power 6, right? You can see the gain. That means one photon of one particular wavelength gives me a gain of this much value, right? So this is what I have made use of PMT. Can I show? Hello? Can I show? This is what I made use of. This is what I made use of PMT. This is from Hamamatsu, a Japanese company. This is structures of pins, which you can see here. This is structure and pins you can see here. It contains photocathode point, it contains dynode structure, it contains anode structures. And now I supply 1000 volts with a divider resistive network onto this, and then this is what photocathode is. This is, please sir, hello, can you show? This is what photocathode looks like. Just this region. Middle one. This is what photocathode looks like. The photon is made to strike onto this, and then it gets. This is how a photocathode looks like. The photons hits this area, and internally it gets amplified electronically through divider resistance network, and gives me the final output. This is PMT from Messer's Hamamatsu, and this detector is being made use of in your analytical instruments, your communication systems, and your fluorescence measurements. All those, wherever the light detection is required, this is being made use of. It is a tube version of the photodetector, right, using photoelectric effect. Okay, sir, thank you. So this is what the photodetector in tube version looks like. I'll switch over to the semiconductor type photodetection mechanism, where again a PN junction is being made use of in this photo detection. In semiconductor, conduction band and valence band are separated by a forbidden band gap energy. Electrons at the valence band are bound, and electrons in the conduction band are free, and when a small voltage is applied, they move and causes current flow. Populating the conduction band with electrons causes the semiconductor to conduct electric current. The value of band gap determines the conductive properties of semiconductor. Continue. Right? The band gap energy Eg defines what wavelength this semiconductor will. Okay, so you can see this PN junction. It is a P doped material and an N doped material, and in the active region you have a depletion layer. So that depletion layer plays an important role in detection of light. So what we want, that as I said, the internal photoelectric effect, wherein a photon, when it hits this depletion layer, generates a electron hole pair. Now if this electron hole pair, if I make use of my system such that it is made available to the outside media, so I make use of this active region or depletion layer region for my detection. So a PN junction can be formed by diffusing either p-type impurity such as boron into n-type bulk silicon wafer, or a n-type impurity such as phosphorus into a p-type bulk region. And if you see the right side equation figure, you have a p-type material, you have a depletion layer, you have a n-type substrate, and now the light which is falling from onto this gets absorbed in the depletion layer, pass through the p region, gets absorbed in the depletion layer, generates electron hole pair based on the band gap energy of this material, and then this is being made use at the outside of the detector. So this is basically the internal mechanism of photo detections. So you can see here you have again a valence band and a conduction band, and then the band gap energy, if it is greater. Why it is moving ahead in the it's automatically moving. You have a photon, and if it is hitting the conduction and a valence band, having a band gap energy which is slightly more than that. Yes, if it is slightly more than that, it is being absorbed in the depletion layer and creates an electron hole pair. And if it is reverse biased, so you can see this electron is moved onto the N side and holes is moved to the P side, and then at the outside media, outside the junction, it generates a photoelectric current, right? So first thing is that this electron hole pair must be moved out of the junction to generate the electric current. So you have a photo generation of electron hole pair, reverse bias PN junction, and energy band diagram showing the photo generation and separation of electron hole pair, right? So all semiconductor photodetectors use photon absorption in depletion region to convert photons into electrons hole pair and then sense them as a form of photons or light. When a semiconductor is illuminated by light having an energy of E is equal to h nu, whereas h is Planck constant, nu is the frequency of that photon, greater than its band gap energy, e.g. the light is absorbed, and then it creates an electron hole pair. So an incident photon must be passing through P region and will be absorbed by the depletion layer. So the absorbed energy creates electron hole pair. Electron rises to the conduction band from the valence band, and hole will fall to the valence band. The free electron travel down the barrier, and the free hole will travel up the barrier to constitute the current flow. The photon absorbed in the neutral P or N region outside the depletion region creates electron hole pair. If it is not in the depletion layer, if it is in the P or N region, they also create electron hole pair. But then during the process of traversing the depletion layer, it may be possible that it gets recombined with the holes or electrons. So it will not contribute to the photoelectric current outside unless it crosses the junction. So that wherein they reduces the responsivity of the photodetector. So one must understand that the width of the depletion layer should be more as compared to P or N region of the PN junction to get the maximum output, right? So EHP created close to the depletion layer can diffuse and subsequently be swept across the junction by the large electric field or the reverse bias due to applied reverse bias voltage. An external current is produced, but it is delayed with respect to variation in the incident optical power. It is desirable that the photon be absorbed in the depletion layer so that it can contribute maximum in the generation of photocurrent. Typical PN diodes have a rise time of the order of microseconds, making them unsuitable for high speed electric field across the junction facilitated the rise of photocurrent because it gets swept over by the reverse bias. The primary operating wavelength region for fiber optic communication system are 850 nanometer, 1310 nanometer, 1550 nanometer. The photodetectors which are used in the systems are PN junction, fin photodiodes, avalanche photodiodes. So if I see the photodetector IV characteristics curve under illumination, the curves of PN junction is same as we have studied earlier in the elementary classes. The IV characteristics is ID is equal to I sat e raised power QVA KT minus 1, where I sat is the saturation reverse current, ID is the dark current, and Q is the electric charge, VA is the applied voltage, KB is the voltage Boltzmann constant, and T is the temperature. So you can see the curve is similar on the left. Okay. Okay, so ID is the photodiode current, I sat is the reverse saturation current, representing the thermally generated free carrier which flows through the junction. So I total, when a photon is falling onto this junction, the curve shifts downwards linearly. As you see, the IP is equal to R lambda Pi, right? So as the power of this light keeps on increasing, the curve shifts down, right? So that means the curve is now linearly increasing downward side based on the photocurrent or based on the light intensity following on this. So illuminating the photodiode with optical radiation shifts the IV curve by the amount of photocurrent, which is IP, right? So now I can sense IP based on the photocurrent. So this is the equivalent circuit of a photodiode. You have a IPH, which is a photocurrent generated because of the illumination. You have the ID, the dark current or the noise which is coming onto this. The CJ, the junction capacitance of the PN diode. The RSH, the shunt resistance of the PN junction. RS, the series resistance of the PN junction, and the load resistance. And the current, which is IPH, is produced because of the illumination, is passed on to the RL, and it generates the voltage output. Now if I want to operate this at a higher frequency region by CJ, RSH, RS, all these parameters I must consider. So the shunt resistance is of the order of 1000 of mega ohms. Ideally RSH should be infinite, and this is because of the reverse bias diode. RS is the series resistance which arises from the resistance of the contacts and resistance of the undepleted region of the silicon, which is P and N material, and its value is ranging from 10 to 1000 ohm, and this is used to define the linearity of the photodiode. And the junction capacitor, this capacitor is governing my frequency response of the PN junction or photodiode. The junction Some question there? Okay. The junction capacitance is directly proportional to the diffused area and inversely proportional to the width of the depletion layer. Junction capacitance is used to determine the speed of the response of the photodiode. That means the diffused area, the area of the photodiode, and the width of the depletion layer governs the capacitance. That means if I want to operate at a higher frequency region value, my diffused area or the depletion region should be having much larger, whereas the area of the detector should be smaller, right? So the response time is now governed by, of the photodiode is governed by the drift because of the reverse biased, the diffusion because of the electron hole pair which is produced in the P or N region or in the depletion region, it gets diffused, and the TRC region, TRC or the RC time constant of the diode circuit combination. So this governs by the frequency response of the photodiode. I cannot achieve more than that, the frequency response of the photodiode, by using amplifiers or everything. So TRC is around 2.2 of RC, where R is the sum of diode resistance and the load resistance, which is RS plus RL. RS is the series resistance, RL is the load resistance. So the load resistance plays a role defining the bandwidth of the photodiode, and C is the sum of the photodiode junction and the stray capacitance, which is Cj plus Cs, that is the total capacitance, plays a role over here for defining the total bandwidth of this. Since the junction capacitance Cj is dependent on the diffused area of the photodiode and the applied reverse bias, faster rise times are obtained with a smaller diffused area and photodiodes and larger applied reverse bias, because when I apply a large reverse bias, the depletion width keeps on increasing. So maximum depletion region, I get the maximum absorption of the photon. So the total rise time is governed by the T drift, T diffused, or TRC square under root. So that is my limited value of the TR, the rise time of the pulse I can get, or the analog signal I can get from the diode. Based on this, I can govern my further electronics out of this. So if I plot the capacitance versus reverse bias voltage, you can see as the reverse bias voltage keeps on increasing, the capacitance of the photodiode decreases. That means my frequency response keeps on increasing. So if I understand the photodiode characteristics of this, I can say responsivity, the responsivity versus wavelength, right? Because the responsivity of the photodiode changes with the wavelength, right? As we have seen in the earlier case also, there is a change in the light output versus the wavelength. Same is the situation here. The responsivity, the response of band gap is varying with the wavelength. The responsivity of the silicon photodiode is a measure of the sensitivity to light and defined as the ratio of photocurrent IP to the incident light power P at a given wavelength. So this is R lambda is equal to IP by P. R lambda, which is the responsivity, varies with the wavelength of the incident light as well as applied reverse bias and temperature. It is a measure of the effectiveness of the conversion of light power into electrical signals. You can see that at 900 wavelength on the left side, you can see the responsivity is of the order of approximately 0.6. That means if a photon is falling onto this, only 0.6 times the current, photocurrent, is available to me. Not all is converted into photocurrent. So responsivity variation to change in temperature is due to decrease or increase of the band gap because of increase or decrease in the temperature respectively, right? This is how it is showing that the wavelength also is varying with versus the temperature. So I must control the temperature of the photodetector while operating in this system. The quantum efficiency of this photodetector is defined as the fraction of the incident photon that contributes to the photocurrent, and that is number of emitted photons to the number of incident photons. And one of the major factors which determine the quantum efficiency is the absorption coefficient of the semiconductor. So because the semiconductor which we are using will not absorb all the photons, it will absorb a partly of that and used within the semiconductor. So it is always less than 1 or 100%, Right? Maybe say 85%. That means 85 electrons collected per 100 incident photons. So 85 photons contributed to the electrons. So the responsivity of or the quantum efficiency is related to R lambda Hc lambda q. You can see the quantum efficiency is related to the wavelength, and responsivity is in the terms of ampere watt. So responsivity and quantum efficiency, if you plot versus wavelength for different materials, because the band gap is different, because the energy of the photon is different. You can see for silicon it ranges from 0.6 to 1. Beyond 1 the absorption of silicon is deteriorated, and the light response. That means I cannot use a silicon photodiode beyond 1 micron or 1000 nanometer wavelength. I can use indium gallium arsenide, which is going up to more than 1.7 micron or 1700 nanometer, and that is effectively giving me more than 0.9% of responsivity and efficiency. Germanium is around 1.6. So that means based on the material of the semiconductor or PN junction which I have been using, I can get the response of the photodetector. So quantum efficiency is not constant at all wavelength. It varies according to photon energy. For a given material, as the wavelength of the incident photon becomes larger, the photon energy becomes less than that required to excite an electron from the valence band to the conduction band. Responsivity falls or rapidly beyond cutoff wavelength. Like silicon, I cannot sense beyond 1 micron or 1000 nanometer. So that means for beyond 1.1 micron, I must go for either indium gallium arsenide or germanium photodetector. So you can see that why this situation is arising. You can see the reflectivity of silicon. Because we are using as a PN junction, because if it is silicon based photodetector, the reflectivity in the lower region is much higher, right? 0.7 or 0.8. Same way the absorption coefficient of silicon is much higher or lower at the 200 to 400 nanometer. That means between 400 to 1100 nanometer or 900 nanometer, I can efficiently use silicon photodiode, right? So the reflectivity of polished silicon wafer is determined from the complex refractive index. The light is absorbed exponentially with distance and is proportional to the absorption coefficient. The absorption depth is given by the inverse of the absorption coefficient of or epsilon alpha minus 1. Absorption coefficient of semiconductor material is strongly dependent on wavelength. That means the wavelength and the absorption coefficient and the reflectivity of the material is governing the total in totality what should be the detected wavelength range for any particular photodetector material. So once we have the photodetector, how to bias that photodetector, I can make use of without biasing, without applying any voltage across it, because I can use it as a either in a reverse bias mode or in a without reverse bias. So in a situation where I am not using any reverse bias, I have just connected the cathode of the photodiode to the ground level, and then the light, if it is falling onto this, is generating a photocurrent, and this photocurrent is made to pass through the RF feedback resistance, because bias current over the op-amp is much smaller, and then this current is now multiplied by the RF, the feedback resistance, and gives me the output. So this type of photodetector or photovoltaic mode of operation, it is called, is unbiased. That means I am not applying any reverse bias onto this, is being made use of when I want to detect low light level applications, or linearity is main important factor here. Here the noise is much smaller as compared to the bias mode of photodetector operation, and the stability or the bandwidth of this is governed by 1 over 2 pi RF by CF. CF is the feedback resistance which I have applied across this, just to avoid the ringing operation across the amplification of that, and CA is the capacitance at the junction of the amplifier. So FOP defines the operating bandwidth in this case situation. I can operate this up to a kilohertz region or so region, right? Another area is the photoconductive mode of operation. When I apply photodiode with a reverse bias, say minus 30 volt or minus 15 volt, like that. So reverse bias creates a depletion layer, increase in the width of the depletion layer, or decrease in the junction capacitors, but there is an increase in the dark current and the noise current, and there is a decrease in rise time. So when I want to operate it for a higher bandwidth operation, so I can use a reverse bias photodiode for high bandwidth of operation. So the GBP, or the gain bandwidth product of this, you can see here the F3dB maximum of the bandwidth of this type of configuration is given by 2 pi RF CJCFCA under root. That gives me the 3 dB operation of the photodiode. That means the photodiode first, the junction capacitance, the reverse bias, the operational amplifier, GBP governs the what is the maximum bandwidth I can make use of, I can achieve using this configuration. So the noises which is available in the photodiode I must consider, because the light output which is available to me by the through the optical fiber is very low or very feeble. The noises in the photodiodes system affects the detection mechanism. So what are the noises available in the photodiode? The short noise, thermal noise, 1 over F noise, all these noises they restrict my operation of low detection of the light level. So short noise is generated because of the statistical fluctuation in both the photocurrent and the dark current, and is governed by under root of 2q IP plus ID delta F. That means the bandwidth of the input signal is also related to the short noise, and the dark current and the photocurrent also generates the short noise. So that it's a statistical fluctuations. So by increasing the photodiode current, I can control this short noise, and this is the dominating source when operating in the photoconductive bias mode or reverse bias mode. Another noise is the Johnson noise, which is thermal noise. Every resistance is associated with a temperature fluctuations, and that generates a noise inside it because of recombination of electrons holes inside that. So IJTH, the short noise, is governed by under root of 4 kb T delta F RSH. You can see the short noise or the thermal noise is related to under root T and the bandwidth, and inversely proportional to the shunt resistance or RSH or load resistance also. So this RSH is the shunt resistance of the photodiode. This type of noise is dominant current noise in photovoltaic mode of operation, where the feedback resistance or RL we can continue to increase to get the lowest detection of the light level. All resistors have a Johnson noise associated with them, including the load resistance. So the figure of merit parameters, what defines my detection mechanism, figure of merit, is used to assess the noise performance of the optical detectors. Most commonly used are noise equivalent power, detectivity, and specific detectivity. Suppose when the market so many detectors are available, which detectors I must consider? So I must consider these parameters. Besides the wavelength, the responsivity, and the quantum efficiency, I must consider these parameters also. So noise equivalent power says what is the minimum signal level, input light level I can sense, which is equivalent to the RMS noise which it can generate in a 1 Hz bandwidth of the detector, and this is essentially the minimum detectable power below which I cannot detect. Another domain, another specification is the detectivity, which is inverse of 1 over NEP, which is characteristics detectivity. Another area is specification is specific detectivity, because the dimension of photodiode is varying, right? You can have a larger diode active area or a smaller diode active area. So how to compare that? So that is now a specific detectivity, which is D by multiplied by under root A, which is area of the photodiode active region in a 1 Hz bandwidth. So that is more used currently. So D star allows, or specific detectivity allows, different photodetector to be compared independent of sensor area, and system bandwidth, a higher directivity value indicates a low noise device, right? So this is how a PN junction behaves. As I said earlier, that I want my depletion layer to be the maximum width. No? Because if the width of the depletion layer is more, that means my detection region becomes more, right? I don't need P or N layer to be having much larger width. So what is being done? An intrinsic layer between P and N junction is being sandwiched, and that intrinsic layer absorbs the maximum electron hole pair, maximum photons, which thereby generates the photon electron hole pair, and that is being driven by a reverse bias on this. If you see the structure of the pin photodiodes, you have a top metal contact, you have a p diffusion layer, you have an intrinsic layer, then you have a n-type material, you have an n plus contact layer, and then this shows a photodetector with a coupled fiber optic cable. The P intrinsic N structure decreases the distance between the P and N conductive layer, decreasing capacitance, increasing speed, because once I have a more depletion layer, the speed becomes much more because of decrease in capacitance. The volume of the photosensitive region also increases, enhancing the photoconversion efficiency, and the bandwidth can also be enhanced to tens of gigahertz region. That means I can now make use of this photodiodes or pin photodiodes for high sensitivity or high speed operation, right? Operations. So I have a pin photodiodes with me here.
वो डायोड दिखा रहा है तो चल क्यों नहीं रहा इंटरनेट तो चल रहा था ये भी तो चल रहा है नहीं इसको रिफ्रेश कर दो ये रिफ्रेश चलने तो हो गया अपने आप आ जाएगी बात सीधे बैठ जाओ तुम म्यूट नहीं हो शायद
And P-type material, top of an undoped contact layer. That light should be absorbed in the depletion layer region of the diode to ensure that the electrons and holes are separated in the electric field. This implies that a depletion region larger than the absorption length must exist in the detector. This is easily assured by making the absorbing layer undoped on only a very small voltage is required to deplete the undoped region. And the added advantage is that the recombination generation time constant is longest for undoped material, which provides a minimum thermal generation of current. That means the noise is limited here. Pin photodiodes has a lesser noise. Now I switch over to the next domain, which is avalanche photodiode. Another domain is it has multiplicative, where one photon gives me 10 raised to the power 4 or 10 raised to the power 6 electrons. Similarly, in the semiconductor, avalanche photodiode has come into the picture, where the one photon amplified is converted into a 10 raised to the power 4 or 6 electrons. So this mechanism is achieved by applying a high voltage, high reverse bias across N and P region, and then you have a N region, you have a P region, you have an intrinsic region, you have a P plus P dot region. Now at the N and P region, the intensity profile for electric field, you can see is much larger. This is much larger. The voltage which I applied, maybe minus 100 volt or so, is maximum is available in this region, and lower value of this is available in this region. Right? So intrinsic layer is mainly used for absorbing the photons. Once these photons generates the electron hole pair, they move to the respective electrodes. When they move to the respective electrode, because again a high voltage is appearing, a high reverse bias is appearing, so they now hit this electron structure of the junction and then creates a secondary electrons, or a avalanche phenomena which takes place between this region, right? And then it gets multiplied. The electrons is liberating more and more electrons in this high gain region of the electric field by getting the more kinetic energy and disrupting the lattice of this. So this is the basic principle of avalanche photodiode. So photodiode will internally multiply the primary signal photocurrent before it enters the input circuitry of the amplifier, increases receiver sensitivity. The photocurrent is multiplied before encountering the thermal noise associated with the receiver circuit. For carrier multiplication, the photogenerated carrier must traverse a region where a high electric field is present. So this is how the semiconductor device fabrication generates a high gain electric field region within the photodiodes, which I have shown to you. In the high field region, a photogenerated electron or hole can gain enough energy, enough kinetic energy, so that it ionizes bonds in the valence band upon colliding with them, because they get more kinetic energy. And this newly created carriers are also inflated by the electron. Cause further impact ionization. This phenomenon is called avalanche effect. Creates an extremely high electric field in the region, which is of the order of 3 into 10 to the power 5 volt per centimeter. You can see within that short region of the PN junction, this type of electric field exists. So that means the electrons which is generated, or photoelectrons which is generated in the intrinsic layer, gets accelerated by such a large amount of electric field and generates impact ionization and avalanche effect. So it requires high voltage of the order of minus 100 to minus 400 volts in order that new carriers created by impact ionization. So it generates a gain of 10 raised to the power 4 of the order of for one photons. Again, this ionization is again a random phenomenon, isn't it? Because one electron may hit may create this type of increasing gain 10 raised to the power 4. Another one may create a 10 raised to the power 3 gain. So that means there is a fluctuations available at the output of the photodetector, right? So that means there is a statistical noise available at the APD system. So when carriers are generated in undepleted material, they are collected somewhat slowly by the diffusion process. This has the effect of producing a long diffusion tail on a short optical pulse. When the APD is fully depleted by employing high electric field, all the carriers drift at saturation limit velocity. The response time of this device is limited by three factors: the transit time of the carriers across the absorption region, that is depletion width; the multiplication factor, how much time it takes; the RC time constant at the junction capacitance, because of the junction capacitance of the load. At low gain, the transit time and the RC effects dominate, giving a definitive response time and hence constant bandwidth for the device. At high gain, the avalanche builds up, time dominates, and therefore the device bandwidth decreases proportionally with increasing gain. You may get more gain, but the bandwidth decreases. The rise time between 150 to 200 picosecond has been achieved. In this case, APD one can use for a very short duration for very large bandwidth applications, and fall time of 1 nanosecond or more are quite common, and this limits the overall response of the device. The multiplication factor is a measure of the internal gain provided by the APD and is given by IM by IP, where IM is the average value of the total multiply output current and IP is the primary photocurrent. That means one photoelectron, and IM is the total multiplication. The avalanche mechanism is a statistical process, as I said, and not every carrier pair generated in the APD experiences the same multiplication. Thus, the measured value of M is expressed as an average quantity, which is as great as 10 to the power 4. Now, I want that the reach through region or the PN junction should have a minimum width, so that my enhancement of the electric field I can increase. So, if I make my width of this junction much smaller, my enhancement in the electric field is much larger, and then the carrier multiplication takes place much faster. That means I can increase the width, I can increase the bandwidth of the APD. So another device, which is silicon reach through APD, has come into the picture to ensure carrier multiplication without excess noise for a specific thickness of multiplication region within APD, necessary to reduce the ratio of ionization coefficient for electrons and holes. And Kh is a strong function of electric field, which is ionization coefficient, which is of the order of 0.1 at 3 into 10 to the power 5 volt per centimeter inverse, to 0.5 into at 6 into 10 to the power 5 volts per meter inverse. For minimum noise, the electric field at avalanche background must be as low as possible. That means a smaller K value I must consider, and the impact ionization should be initiated by the electrons. This limits the transit time and ensures a faster response. This is how the fabrication looks like, that you have a intrinsic layer, you have a P layer, you have an N layer. Again after this threshold only the avalanche multiplication takes place, not below this electric field. That means I have now limited my electric field enhancement only to a certain, beyond a certain electric field region, which gives me the multiplication, otherwise it will not give. So this is where the silicon reach through APD mechanism has come for generation of these devices, right? So this is the gain region, and this is the absorption region, which is of the order of 50 micron, and this is very small. The high field region, where avalanche multiplication takes place, is relatively narrow and centered on the PNN plus junction. Under low reverse bias, most of the voltage dropped across the PN junction. When the reverse bias voltage is increased, the depletion layer widens across the P region until it reaches to the nearly intrinsic region, pi region, which is called. The pi region is much wider than the P region, and the field in the pi region is much lower than the PN junction region, because I want avalanche multiplication to take place here and not here, right? Because I want my transit time to be shorter and shorter. So thus this has the effect of removing some of the excess applied voltage from the multiplication region to the pi region, giving a relatively slow increase in multiplication factor and applied voltage. So a fast response of 0.5 nanosecond has been achieved in this case. That means bandwidth of more than gigahertz is possible using this type of APDs. So advantage is that I have a sensitivity of the order of 5 dB to 15 dB over pin photodiodes. That means I have a very low level light level detection, wider dynamic range as a result of their gain variation, with response to time and reverse bias. However, the drawback is that there is a slightly complex fabrication involved in this, and the random nature of the gain mechanism, which leads to additional statistical noise available to this, and often the bias voltage is much higher as compared to pin photodiodes. So the variation of gain multiplication factor with temperature is also has to be taken into consideration. That means I must have a temperature compensation system available into this. So this is how a photodetector specification looks like silicon, germanium, indium gallium arsenide. Their wavelength range 400 to 1100, 800 to 1800, 900 to 1700, and the peak wavelength, how it is available to me. The responsivity 0.6, 0.65, 0.7, 0.63 to 0.8. So Indian gallium arsenide in this region gives me much better responsivity and quantum efficiency. And if I see the rise time, because the bandwidth is the prime concern, if I want to go for a higher communication speed, you can see here the 0.5 or 0.06 is the region rise time for indium gallium arsenide photodetectors, pin photodetectors. So again, I can stack this number of APDs in a structure wherein I can have number of APDs in a rectangular patterns. Now this pattern is called MPCC, multi-photon silicon photo multiplier, multi-pixel photon counter. It's a new type of photon counter wherein a small device, a small light intensity I can amplify using a APD, number of APD in terms of a two-dimensional imaging. This type of structure is possible if I can make on the XY direction the small APDs, and the light input which is falling onto this in the rectangular pattern or image pattern, I can sense the brightness or intensity profile of that image. So this is used in fluorescence, lifetime imaging, PET, positron emission tomography, single molecule detections, in biology also. So this type of detectors is having application in a different domain. Another area is charge coupled device. You might have seen in your mobile, in your camera, the CCD is a common factor which grabs your image, your two-dimensional intensity profile, and convert it into a electric pattern and pass it to the outside media. A typical CCD looks like this. Now the color CCD is having this type of pattern of color filter, red, green, blue color mixing filter onto the each pixel. When I say, you can see this pixel, this each of this pixel is having this type of filter available to this, and the green filter is, or green pattern is twice as much as red and blue filter because of eye sensitivity to the green light. So when light falls onto this, only green portion, you can see you have a blue filter here, you have a green filter here, you have a red filter here. So only red filter pass on to the red wavelengths, green pass to green, and then you create a RGB profile of the electrons based on the intensity profile. And this is how the CCD looks like. You have a different pixel structures. It's an array of matrix. It's an array of matrix. On each pixel you have a lens. On each pixel you have a lens, a micro lens fabricated onto this. The light which is falling onto this is made directed to the pixel or photo detection area. Now this photo detector area generates a charge or photo charge accordingly. Based on this, now you can understand the mechanism of this, that onto this array, the light which is a two-dimensional light pattern, or the image pattern, or the photograph which you have grabbed, is passed on to this array pattern. Each of this array pattern, each pixel of this array pattern generates a photocurrent. Now I want this photocurrent to be read at a much higher rate so that I can project this in the form of a image. You can understand this, that these are the pixels wherein a charge or photocharge is generated, and this is your vertical pattern where the charge is rolled out. So all these patterns, this array pattern of this row is rolled. You can understand that there is a conveyor belt on the horizontal direction and there is a conveyor belt on the vertical direction, and this conveyor belt on the vertical direction rolls one by one and pour that charge to the horizontal conveyor, and this charge is now transported to the amplifier output here. So that means this charge is first made to available here and then outputted to the amplifier. Next charge is rolled here and then outputted here, and this is how the CCD output is being read in the terms of electrons. So you can understand how the pattern looks like. You can understand that there is a pixels. Each pixels is now hooked to a conducting material wherein I apply a voltage. Suppose this is by pixels. I have applied 2 volt, 2 volt, 2 volt, 12 volts here. I want to read this pixel charge. This is the charge accumulated underneath this pixel. So what I will do, I will make this 2 volt as 10 volt. So now this charge is made available under both the pixels. Now I make this 10 volt as 2 volt, and this charge is now slowly drained to this pixel region, right? This pixel region. So this is how from one pixel to the another pixel I can roll out. So this clock pulses which I am showing here is ranging from 2 volt to 10 volt so fast, of the order of gigahertz, that I can read this pattern in 50 milliseconds for your 50 hertz signal. So I can read this charge through this my electronics, and that I digitize this output to the communication point of view. I can transmit images, I can transmit video using this sensors. So working principle is you have a generated charge using photoelectric effect, which is internal photoelectric effect. You have collected the charge under the pixels, you transfer the charge, apply a differential voltage across these gates, and then the electrons moves, and through vertical resistors I pass it to the horizontal resistors and read out at the output. So advantages on the CCDs, their quantum efficiency is much larger, 80% low noise, high dynamic range. That means different voltage level I can sense, different amplitude level of the light intensity I can sense, high photometric precision, very linear behavior, immediate digital conversion of data, low voltage, and rapid clocking. And you have seen that in astronomy also one can grab the images through this. Now I'll just switch over to the slight different topic, which is optical signal detection techniques. The signal, the light amplitude or the frequency or the phase which is available to me at the photodetector, I want to detect it. I must consider both signal and as well as the noise. The noises which is available is Johnson noise, short noise, 1 over f noise, or pink noise, which is more dominant at the lower frequency region. Stray light, a noise which is hindering to the optical system. Light source fluctuation, or the fluctuation which is at the source point of view. Drift, capacitive coupling noise because of the cables running, all those things. All these noises one must consider, one must add together and define what should be the signal amplitude or optical signal amplitude is required at the detector end, so that I can amplify that signal. So detection mechanism or detection techniques are time averaging. I can average this number of times so that the noise gets out of the system, and because the noise is incoherent, so they average to 0. Or a lock-in amplifier techniques or a ratiometric techniques. A lock-in amplifier is something where you use synchronous detection, a ratiometric technique wherein a portion of the source is also being fed it to the ratio of the detection mechanism. So optical receiver, if I see, it converts the optical signal to electrical domain, and I want to recover this data. So I have an optical input. I can amplify this optical input either using EDFA or another amplifier. I have a photodiode which is biased by a supply. I have a pre-amplifier, amplifier, low pass filter, and a decision circuit that whether the thresholding is required or not required, at what level it is required, and when it is to be clocked, and then the final data in the form of a digital output, I can get it. So this is what a lock-in technique is shown here. This is for a line of sight amplifier systems, line of sight detection system. The same technique can be applied for a photo detection mechanism. You have a transmitted light, you have a beam combiner here, wherein the light coming from this transmitted signal or a optical fiber is now merged with the one of the light from a local oscillator, one of the optical light signal from a local oscillator, and now these two signals are combined at this point and made it to fall to the detector. Now this detector is now generating a multiple frequency components, which I now filter from this. Now this has a mechanism wherein I can increase the local oscillator amplitude or voltage so that I can get the maximum signal to noise ratio. So this is where the optical receiver or coherent detection technique has worked for this type of photodetectors. So this is what a small mathematics shows on optical coherence detection. You can think of a signal to be E signal cos omega signal T phi, another local oscillator signal which is having slightly different frequency omega L naught with a E L naught as the amplitude. This is the signal amplitude. If I both these signals are multiplied at the detector output, if these signals are multiplied at the detector output, the amplitude is proportional to your square of the amplitude. The output intensity is proportional to the square of the amplitude. If you square this, it generates 2 omega signal components, 2 omega local oscillator signal components, sum of the frequency component, and difference of the frequency components. So that means the higher frequency components now I have passed through a high frequency filter, so I can filter out this signal. And this is a DC component which is E signal and E local oscillator amplitude. I can filter out using a capacitor. So what is left here? E signal, E local oscillator, omega signal, omega local oscillator, and phi, right? So this is the signal which is available at the detector output by multiplexing, by impinging two signals right at the detector inputs. So now if the omega signal and omega local oscillator frequency are same, right, this component goes to 0. So that means the cos phi terms is coming into the play. That means coherent detection is coming into the play if the frequency of both the signals or signal which is coming and the signal which is made to fall from the local oscillator are matched. So that means my signal output of the detector keeps on increasing based on the phi. If I somehow make this phi also constant or phi also matched to the incoming signal or E signal, that means cos phi also goes to 0. Right? So what is left is E signal, E local oscillator amplitude. Now if I increase the local oscillator amplitude, my magnification keeps on increasing. So this is what the technique has been used in my system also at my CSIO for detection of very low level signals with a much higher amplifications with a super heterodyne detection mechanism or a coherent detection mechanism. So this is giving you a brief of detection techniques, noise, the detectors, what is available in the market and how to make use of that. So with this I thank all of you. If you have any query to ask, I'll be happy to reply.
Yes, at Balaji. Yes, at Balaji. Yes, at Nadran Indian.
Any give any feedback?
सर रिस्पॉन्ड तो कर दीजिए नकलन इंडिया इंजीनियरिंग
अंबेडकर इंस्टीट्यूट कानपुर, अंबेडकर इंस्टीट्यूट कानपुर, अंबेडकर इंस्टीट्यूट कानपुर,
Government Engineering College, Bharatpur. Sir, do you have it?
हेलो
हाँ मित्र साहब,
नो मैम हेलो
Yes,
हेलो
sir. Yes, yes.
नो सर नो क्वेरी सर
and Selva Kumar from Kachipuram, Mukesh Yadav from Jaipur, Balaji Engineering College, Jaipur,
No question, sir.
Ambedkar Institute of Technology, Kanpur, Ambedkar Institute of Technology, Kanpur, your hall is empty. Rajkumar Goel Institute of Technology, Ghaziabad. Yeah, yes, we are seeing you.
सर अपना माइक ऑन कर लीजिए हमारी साइड से
माइक ऑन कर लीजिए अपना. साउंड नहीं आ रही है, आवाज.
सर आप अपना माइक ऑन कर लीजिए
माइक ऑफ है आपका, माइक ऑफ है वहां पर सिस्टम में.
उनका आवाज आ रही है,
वो आवाज वहां से नहीं जनरेट हो रही, माइक ऑफ किए हुए हैं.
अदरवाइज सर राइट कर लीजिए कमेंट सेक्शन में वी कैन रीड योर क्वेश्चन है
If you are not getting, you don't have any question, please listen from us. We are thankful Dr. Bhatnagar, who has given the idea about how to generate the light for optical fiber. He has also given the idea how to detect the light from optical sources. Now the next lecture is coming. If the light level is low, how to amplify the light. And that lecture will be taken by Dr. Umesh Tiwari. He is also a scientist, senior scientist at CSIU. So in the second half, we'll meet with the Dr. Umesh Tiwari. And we are thankful to Dr. Bhatnagar.
Thank you.
That he has spared his valuable time. And on our request, he had delivered his lecture. So I am thankful to him. And at 2:15, we'll meet you here again. And I request all the remote centers that please gather your strength to utilize the lecture given by the experienced scientist. Teacher will meet you every time, but scientist will meet you rarely. So utilize his services and his thinking. Thank you very much. We'll meet you at 2:15 afternoon after lunch. Thank you.
Thank you.
Thank you, sir.
Bye.
हेलो हेलो सर आवाज आ रही है, बोलिए आप।
राजकुमार गौड़ इंस्टीट्यूट। हेलो। हाँ जी सर, ठीक है अभी।
हेलो
हेलो
हाँ जी,
हेलो।
हाँ जी।
हाँ जी सर, अभी ऑडिबल हो आप।
हेलो।
हाँ जी सर, आपको आवाज आ रही है हमारी?
हाँ आपकी आ रही, बहुत बढ़िया आवाज आ रही है। तो क्लियर
आपकी
आ
भी
रही है।
सर कल को लैब लीजिएगा, देखिए इसमें प्लगइन्स
क्या?
लैपटॉप अरेंज कर लीजिएगा, ये पीसी में प्लगइन्स बार बार ना वो हो जाते हैं।
ओके ओके, कल सवेरे मैं लैपटॉप ही लगा दूंगा।
हाँ जी हाँ जी।
चलिए, अभी क्या है कि माइक्रोफोन लगाना पड़ रहा है बाहर से।
हाँ जी, वो फिर वो दिक्कत।
चलिए मैं अर्न करवा लूँगा। हेलो।
ठीक है सर
हाँ
अभी।
जी सर, ठीक है ठीक है।
ये बताइए कि अभी अगर मैं लगाना चाहूँ तो अभी लग जाएगा थोड़ी देर के अंदर?
अभी ठीक चल रहा है आपका सिस्टम।
हाँ ठीक तो चल रहा है, लेकिन ये कि क्वेश्चन पूछने के लिए मेरे को बार बार माइक्रोफोन लगाना
आपका
पड़ता है।
क्वेश्चन नहीं होगी सर, प्रॉब्लम रहेगा।
अभी सर फिर आप कल अभी लैपटॉप बोल रहे हो आप लगाने को?
हाँ अगर अभी मैं लैपटॉप लगा दूँ आधे घंटे के अंदर
तो ठीक
तो
है,
आ
आपका सिस्टम मत छेड़िए अभी।
ठीक है, कल सवेरे कर दूंगा मैं पूरा, कोई इशू नहीं। हेलो।
हाँ जी सर।
हाँ तो अब ये म्यूट आपकी तरफ से होता है या हमारी तरफ से होता है?
सर वो आपने दूसरे ब्राउजर में चलाए थे, उसमें चल नहीं रहा था, मौजिला में चलाया था।
ओके ओके, चलिए ठीक है फिर। स्पीकर में आवाज नहीं आ रही।
ठीक है।
2:15 आधा घंटा और है आइए कुछ लगा भी लगाओ
तुम्हें करेंगे तो कोर्स भी नहीं कर रहे अभी एक कपड़े तुरंत कोर्स में अभी आ रहे हैं हाँ सुबह भाई सब मैं बात कर बहुत सारे लोग होते हैं सब तो आप नहीं जाओ कर सकते हो सब जो है लेक्चर नोट्स एक्चुअली
அப்ளை பண்ணதுக்கா முதல்ல கிளர்க்கு பார்த்தீங்கன்னா நான் ஒன்றும் அப்ளை பண்ணவே இல்லையே டேட் முடிச்சு போயிருக்கீங்களா அப்ளிகேஷன் ஆறாது அதுக்குள்ள புரிஞ்சு 6ஆம் தேதி அட்மிஷன் வரும்போது அந்தாச்சு 12ஆம் தேதி வந்து பார்த்தீங்கன்னா 14 area, 58. I think that's that correct. Yeah, research number
இங்கே கொஞ்சம் இந்த ரைட் கூட பேஸ் தெரியுங்க சும்மா ஏதோ அதே மாதிரி நம்மள அவங்க பார்ப்பாங்க. இப்போ நம்ம ஸ்பீடில் இருந்தாலும் இதெல்லாம் நமக்கு தெரியல சார். சரிங்களா? நம்ம என்ன பண்ணால் அவங்களுக்கு தெரியும். அதே மாதிரி நம்மள அவங்க பார்ப்பாங்க. இப்போ நம்ம ஸ்பீடில் இருந்தாலும் இதெல்லாம் நமக்கு தெரியல சார். நோ சார், தேங்க்யூ சார். நம்ம என்ன பண்ணால் அவங்களுக்கு தெரியும். அதே மாதிரி நம்ம அவங்க நம்ம ஸ்பீடில் இருந்தாலும் இதெல்லாம் நமக்கு தெரியும் சார். No sir, thank you. நம்ம தான் பண்ணா உங்களுக்கு
Yes, sir.
लोग आ गए, जुड़ गए ऑल?
Yes.
Good afternoon.
Good afternoon, sir.
Myself Umesh Tiwari. So I'm going to deliver a talk on optical fiber amplifiers and sensors, trends and application. So the content of this talk is introduction. So in the introduction I'm going to cover some of the basic fiber optics, the propagation of light, then a little bit of the optical communication, why it is important, where what is the bandwidth requirement, all those things. Then I have to touch optical fiber amplifier basics, because I have 2 lectures. So tomorrow I'm going to discuss details of amplifiers. So today I'm just touching the basics of the optical amplifiers. Then I have also planned to talk on optical fiber sensors, then some of the application of the fiber optics beyond telecommunication, and all, as you all know, like fiber optics is the lifeline of internet. So with this content, so I'm just covering what is optical fiber basically. So you all know, like optical fiber consists of core, cladding, and there are so many jackets to provide the strength and
Excuse me, sir.
yeah.
Sir, we are hearing dual sound here. Actually, some of the center has on their mic.
You are not getting
Sir, we are getting to dual sound, sir.
dual sound.
Dual sounds, sir. One sound from you, one sound from other centers. Might be Noida center.
Sir, what about now? Now
It's okay.
Yeah, now it's okay, sir.
Okay. So can I go ahead?
Yes, sir. Please.
Yeah. Okay. Thank you.
Thank you, sir.
So this is all just to cover, just to show you that some of the basics of the optical fiber. So you know, like the light is propagating in the core, and it is the center of the optical fiber, and it is made of the silica doped with germanium or boron. Then surrounding the core is called the optical cladding, and which is made of the pure silica. The difference in the material between core and cladding is important, as you know, because without cladding we can't get the total internal reflections. Then we have a buffer materials which is helping the shield the core and cladding from the damage. It made of the polyimide and acrylate material. Then strength materials also help to prevent from the stretch problems when the fiber cable is pulled and when it is laid down or buried in the inside the earth. And then outer jacket protect against the abrasion, solvents, and other contaminants. So just a brief introduction. What optical fiber communication system is like, we have an information source. It can be data, it can be voice, it can be video. Then we have a optical source which is modulated by these information sources. Then we have a modulator, and then this modulated signal, or you can say that these strengths of pulses in form of pulses, it's propagating inside the optical fiber, which is which also called a channel, and then it is going to the photodetector optical processing unit, and then going to the user. Then you can see there are two kind of optical communication system: analog system, so where the information is transmitted in the form of analog, and it is also received in form of analog only. You can see there are some of the distorted as compared to the transmitted signal, and it is because of there are so many effects in the optical fiber, like dispersion, attenuation, distortion, all those things. So information presented by the analog waveform. Then also one can present the information in the form of digital bits. So this is also just a representation by the binary in the form of the binary. Then why optical fiber? So all you know. Anybody?
they just connected.
Who?
Continue.
Okay. So we know, like optical fibers provides very high bandwidths with the low losses. So then 10 Gbps over 100 km, a single fiber, single transmission wavelength without amplifier. More than 200 gigabit using multiple wavelength carriers, like the which is called the DWDM, and then more than 20,000 km at 10 Gbps using optical amplifiers. So when we are going for long haul communication, long span, we need amplifier. Then we know, because optical fiber is made of the silica glass, so there is no effect of EMI, RFI interferences. It has very small size. The total size of the optical fiber is 250 micron. It has very low weight, and it increases the data security because the information is propagating inside the core. so nobody can tap the information, so information is highly secure. Then I just little bit describe refractive index profile of the optical fiber. So it is also very important. So I have just try to give an introduction. So there are different refractive index profiles people can design. It can be linear, it can be triangle, it can be square. So basically all we know only that step index profile and graded index profile, but one can design as per the requirement triangle, and so many other designs also available and already demonstrated by the researchers for different applications, like where people are making low band losses and then amplifiers, then for the gain flattening fibers. So people have already presented different kinds of. Any question?
No, sir. Please connect to it.
Okay. So core reflective index is N1, it is represented. Core cladding is the N2, and I have already explained why different profiles, because in multi-mode fiber, as you know, the reflective index profile, if it is step index, we have a more dispersion. If it is a graded index, we have a less dispersion. So I'm not going to cover the dispersion, so dispersion will be covered in the next lectures. So you will get the flavor on that also, why the reflective index profile is important. And then I'm going to cover just little bit of the total internal reflections, because you know the light propagating in the optical fiber through the total internal reflection. So when you can see here also in the this presentation, so there is a incident angle that is denoted by theta I, and then there is a transmitted angle theta T. So we have a core and cladding. So core is having the higher reflective index and the cladding is lower reflective index. So as the light is incident on the core cladding interfaces from higher to lower reflective index, and as you can see here, so as theta is increasing, so you see the light is going to the towards the interface, and the transmitted angle is also increasing until the theta T become the 90 degree, and as soon as the theta T is 90 degree, so and the value of the theta I is equal to the 90, it is called the critical angle. And when the angle of the incident light is more than theta C or critical angle, the light is reflected back to its original medium, and it is called the totally internally reflected. So this is the principle of the light propagation inside the core of the optical fiber. Then so it was a just pictorial presentation. Here also you can see in the fiber also, if the theta 1 or it is an incident angle is less than critical angle, the ray is reflected or reflected, and which is also we are calling it is a lossy ray or reflected ray, and it is not coming to the fiber and we are getting the losses. And if the theta 1 is more than the critical angle, ray is totally reflected. Another parameter is the numerical aperture. Numerical aperture is also very important, because numerical aperture is as a quantity which is measuring the total gathering power of the or ability of the gathering of light of optical fiber. So there is a, it's called angle of acceptance, and it is denoted by the difference of the n1 square to the n2 square. So that if the numerical aperture is high, the optical fiber can gather the more light. Then fiber materials. What are the fiber materials? So you know, like the material is this SiO2 silica, but we all know the silica is the core of the silica optical fiber is doped with the germania and phosphorus, boron, fluoride to enhance the reflective index of the optical fiber. So to get the total internal reflections, So the glasses and plastics the fiber are made of. So you can see the N is 1.458 at that, because the refractive index depending upon the wavelength. So variation of the refractive index as a function of doping concentration in the silica, you can see in the pictorial representations. Like if it is doped with the germania, the refractive index is at this side, and if it is doped with the boron and fluoride, so it is coming downside. Then it is the whatever I have represented, it is a ray theory, but in a single mode fiber the information is propagating in the form of wave. So you see they are called the mode. So the wave representation of the mode is basically nothing but they are the solution of the Maxwell equations which satisfy the boundary conditions, and there are finite number of guided mode and infinite number of the radiation or leaky mode. So you can see TE0, TE1, TE2, so they have their own way of representations how they are propagating inside the waveguide or optical fiber. So these are the representation of the leaky mode. When the information or light is leak out due to certain reasons, they are called a leaky mode, because the light or the mode which is having the oscillatory solution in the core, they are called the guided mode, and exponentially decaying in the cladding. So the light or the power which is going to the cladding, it is also called the evanescent field. And you can see in the guided mode there is no light is going to the cladding, and light is 100% transmitted. There are certain parameters as I have already mentioned. So numerical aperture, it's a very important information if you are going to buy or you are doing the research on optical fiber. So whenever you are purchasing optical fiber or maybe characterizing optical fiber, numerical aperture one has to measure whether whatever it is mentioned in the specification sheet, whether it is a same value or not. So numerical aperture, then relative core cladding index difference. This is also very important, because delta is difference between the refractance the core at cladding, and which is important for the weakly guiding approximations. So some of the fiber it is 0.01%, in some of the fiber 0.03%. so this is the kind of refractive index difference. Then one of the most important parameter is the V value or normalized frequency of optical fiber, which tells whether the optical fiber is single moded or multi-moded. So the V is defined by the 2 pi by lambda. Lambda is the wavelength of light, A is the core radius, and N1 minus N2 whole square under root. So this is basically numerical aperture. So 2 pi by lambda into A into Na. So if the V is less than 2.4045, so the fiber is single moded. Then we know like there are different optical fiber multi-mode and single mode. So you can see here I have just to give a flavor. So what is the multi-mode? There are multi-path of the lights which is traveling inside the optical fiber. One can use the source as a LED, because multi-mode fiber have higher numerical aperture and it is easier to couple the light in the multi-mode fiber. So that is why LED and white light source can be used in a multi-mode fiber. The core size is varying from 50 to 62.5 micron diameter. The fiber which is the core and cladding both is silica in multi-mode, but multi-mode fiber is also available up to 1000 micron of and more than 1000 micron of diameter, but their cladding is plastic cladding and core silica. So and the cladding is 125 micron, outer jacket is similar to 250 micron. In single mode fiber we are using laser for the information to propagate. The core diameter is 5 to 9 micron diameter. Cladding diameter is similar to the multi-mode fiber. The outer jacket is also same as the multi-mode fiber 250 micron. The thing is, only the major difference is the dispersion is very less in single mode fiber as compared to the multi-mode fiber. Multi-mode fiber generally used for the local area network purposes within the building or within some small localities to carry the information, or for the internet application on all those things. I have just presenting a optical fiber in communication, like technological overview of optical fiber transmission. So as you can see, it started around 1980 after the invention of the laser and optical fiber, and in the initially the speed is, or link capacity is very less, 100 Mbps, 1 Gbps, and as the first invention becomes like due to the EDFA, erbium doped fiber amplifier, and wavelength division multiplexing, now we are able to transmit the capacity like 100 Gbps and even 1 terabit per second. So it is called the first innovation when the EDFA and WDM become the important, and the optical power limitation and bandwidth limitation of the optical amplifiers are there up to 100 terabit. But if you wanted to go beyond the 100 terabit, then we have to go for the second innovation, and that is multi-level coherent transmission, multi-core fiber. Now already people are working on multi-core fiber and how you can control the multi-modes. So within a one fiber there are so many modes. So if you control multi-modes, so each mode can be carry the transmission of lot of transmission. These are some of the differences between the copper cable and fiber. If you can see that differentiate the bandwidth of the copper and the fiber. So in fiber 2.5 kilometer copper is carrying 1.5 Mbps and voice channel is 24. But if you are we are using the optical fiber, the 200 kilometer 2.5 plus Gbps, 32,000 channels plus. So this is the capacity, or you can say this is the impact of the optical fiber. Then why we need a lot of bandwidth? So like there are everywhere now we are demanding the bandwidth for business, multi-service networking, voice, video, business lines, e-commerce, shopping, banking, internets, consumer internet services, remote access, outsourcing, mobile and tele workers, wireless, voice and data services. So we are all using the lot of downloading, and we want so even the Gbps file can be downloaded in a second. So we need a very high bandwidth. Now I'm moving to the dense wavelength division multiplexing. So how this bandwidth or huge bandwidth is possible? So the huge bandwidth is possible if we can arrange all the wavelength in a very smaller, or we can pack all the channel in a very smaller spacing. So they are the terminology like if the wavelength difference is 0.8 nanometer, this is called the WDM, and if the channel spacing is 0.4 and 0.2 nanometer, they are also defined in terms of the gigahertz. So if 100 gigahertz is correspond to the 0.8 nanometer channel spacing, then 50 gigahertz and 25 gigahertz, they are called the DWDM. The channels are very closely spaced, so then you can send a lot of information. This is a typical attenuation plot of optical fiber with the wavelength. So the first window is around 0.85, then the second window comes, it is at 1300 nanometer, third window is 1550, it's a center wavelength. So you can see from here also the losses are very high for the first window. The 1300 also the losses are quite high. In the third window losses are very small, 0.2 dB per kilometer at 1550 nanometer band wavelength window. That is why all the optical fiber communication is taking place at 1550 nanometer wavelength window, because all the sources amplifiers, they are easily available at 1550 nanometer wavelength. So what typical optical communication system consists of? It has a transmitter. Our transmitter is nothing but they are the laser diodes. Then we have optical multiplexers. Then we have amplifiers, transmitting fiber. Again we have amplifier. Then we have a dispersion compensation fiber, because there is lot of dispersion in standard single mode fiber. Then again we have amplifiers. And then demultiplexer, and then receiver. So each amplifier, they have their own nomenclatures. The amplifier which is just close to the transmitter, it is called the booster amplifier. And then the power is boosted because initially the transmitter is having high power, so they are called the booster because they are boosting the power, and they are boosting up to the level so that the information can be transmitted without experiencing any loss in the optical fiber. Then we have an amplifier in between the link, which is called the inline amplifier. Then we have a dispersion compensating fiber, which is compensating the dispersion occurred in the standard single mode fiber. So dispersion compensating fiber is also having a lot of losses as compared to the standard single mode fiber. Then we have a amplifier near to the receiver, a demultiplexer. They are called the pre-amplifier, and then we are separating out the each channels and sending to the receiver. So attenuation is basically leads. So because of the attenuation, we need amplifiers for the amplifying the optical signal at regular interval, and dispersion is also is a major problem. Due to that, there is a overlapping of the pulses, and there is a overlapping of the information broadening due to the broadening of pulses. So we can compensate the dispersion to stop this effect. Then this is the like representations. Due to the attenuation, the power is at the receiver is not up to the levels which can detect it, so that we need amplifiers which can amplify directly in a optical domain. And due to the dispersion, each frequency components of the pulses, they are experiencing different group velocity in the optical fiber, and they overlapped and leads to the broadening of the optical pulses. So the attenuation can be overcome either by electronic repeater or optical amplifiers. So these are the electronic repeaters. So these are, I just put it in just to explain what is the advantage and disadvantage. So electronic regenerators, they are called the regeneration. So also it is called the 3R because they are needed regeneration, retiming, and reshaping. They also limits by the electronics. Then only single wavelength can be amplified at a time, and capacity upgradation is difficult and expensive because we are keep on increasing the bandwidth, keep on increasing the capacity upgradations. Now we are talking of the fiber to home, so using the electronics amplifier it is not possible. So as you can see, just differentiation between the amplification and regeneration. So in optical amplifier, the information or the pulses, they are amplified in a optical domain itself. We don't need any intervention, so then our speed is not limited by the amplification process. And in regenerations, first we need to convert the optical pulses to the electrical domain, then amplify them, then reshape them, and then again retime them, and then again convert it to electrical to optical. In this process, it limits our speed and bandwidth. So these are some of the merits and demerits of the optical amplification. So then we don't need any high speed electronics. They are also transparent to bit rate and formats. You can use either any bit rate. Today you can use 40 Gbps, tomorrow you can use 100 Gbps, even after that you can use terabit, petabit, whatever, but it doesn't affect the amplification process. And also format, whether you are using the NRZ, RZ, DRZ, any format you can amplify with the optical amplification. Then it is also possible to amplify multiple wavelength at a time. So it is not limited by the RC time constant of the electronics amplifier. Only the thing is it has a little higher noise because of the amplified spontaneous emission. This is the just a pictorial representation. We have a black box, then there are multiple wavelengths they are coming, and then we are getting the amplified channels. Then what are the desirable characteristics of an optical amplifier? So it should have high gain bandwidth, so that wider range of the wavelengths can be amplified at a time using same amplifier. It should have gain flattening. So flatness is important because all the signal wavelength get same amplified by the same amount, so that otherwise if one wavelength is amplified more, another is less. So it is, if there is cascaded amplifier, so the wavelength which is amplified more at the receiver end, it become 1, and the other wavelength which is amplified less, they become the 0. So then our bit error rate gets affected. So we need a gain flattening. These are the structures. So then what optical amplifier is consist of? So it should have a coupler which is coupling the pump and the signals. Then we have a active medium. It also works similar to the laser. Only the difference is in laser there is a resonator, but in amplifiers there is no feedback or resonator. So we have a pump source, we have active medium, we have a optical coupler, and in the output you can measure either using the detector or maybe optical spectrum analyzer. So there are 3 kind of optical amplifiers. Erbium doped fiber amplifier, so they are based on the stimulated emission from the population inverted medium. Raman fiber amplifier based on the stimulated Raman scattering. Semiconductor optical amplifiers, they are based on the stimulated emission through the electron hole pair recombination mechanism. So these are the 3 different configurations. So based on their deployment, like booster amplifier, inline on pre-amplifier. So booster amplifier I have already explained, it is deployed at the transmitter end. Inline amplifier is deployed in between the link, and the pre-amplifier is deployed at the receiver end to enhance the receiver sensitivity. Then I have to explain a little bit using the energy level diagram how the erbium doped amplifier is working. So you can see, like erbium ions, the optical fiber is doped with the erbium ions. So they are called the specialty fiber. So they are called the doped fiber. So if they are doped with the erbium, they are called the erbium doped. If they are doped with the ytterbium, so they are called the ytterbium doped. Also, if you can dope with thulium, so they are the thulium doped. So there are so many doping constituents are available for different wavelength emission and for different applications. So here, if we are having the erbium doped fiber amplifiers, so there are 2 kind of pump wavelengths are available in the erbium doped fiber amplifier, because it has the absorption at very strong absorption at 980 as well as at 1480. Only the thing is at 1480 it consists the 2 level laser system, and using the 980 nanometer pump wavelength, it comprises 3 laser level system. So people are using both depending upon for what application you are going. If you are making a source of EDFA source, so then you can use a 1480. If we are looking at the 980, so it is good for the amplification purpose. The thing is, when we are pumping using 980, so the erbium ion from the ground state, they are going to the E3 level, that is also called the excited state, and after that they are relaxing to the E2. It is called the metastable state, where the lifetime of the erbium ions are 10 to 13 millisecond, and as soon as a signal with the low amplitude is striking these amplified or excited ions at the excited state, they are coming down to the ground state and releasing a fresh signal with the same frequency and wavelength, and the fresh signal is getting the energy from the excited erbium ion and it gets amplified. So the E2 label is not the single label. If you see with the spectroscopy, so they are very closely spaced label. So that is why we are getting the around 50 nanometer bandwidth using erbium doped optical amplifiers from 1520 to 1570 nanometer. So that is why we can amplify more than 40-50 nanometer wavelength at a time if we are keeping even 1 nanometer channel spacing. 1480 nanometer pump is basically only the problem with the 1480 is it has two level system. So the sometimes the stimulated, instead of the stimulated emissions, the ions are also coming down with the spontaneous emission and it is adding the more noise. So 1480 is not preferred for the amplifier. So what is the basically ASE or amplified spontaneous emission is? So erbium ion is the excited state emits photon spontaneously as well, and this emission is not coherent with the signal because they are coming down not due to the any in the influence of the signal. Like the signal, this spontaneous emission is also getting amplified, and ASE appear both forward as well as the backward directions. Wavelength range is same, 1525 to 1570 nanometer. Power density is 10 to 100 microwatt per nanometer for this ASE. So ASE is represented by this equations. So power of the ASE is the 2 into NSP into H nu G minus 1 into delta B, where NSP is the spontaneous emission noise, that is called the N2 minus N1 by N2. So as all you know, why the noise figure or noise is very high, or it is not less than 3 dB in case of erbium doped fiber amplifier, because even if we can get 100% population inversion, or you can say in other words N2 is very large or very big as compared to N1, so this NSP become 1, and noise figure formula is F into 2 into NSP. So if NSP is 1, 100% population inversion, so the noise figure become the 3 dB. So quantum limit of the noise figure in case of erbium doped fiber amplifier is 3 dB. You can't get less than 3 dB noise figure in theoretically also. So this is called the theoretical limit of the noise figure in erbium doped fiber amplifier. This is a typical emission spectrum of erbium doped fiber amplifier which we have measured experimentally. Then there are some of the equations which is need to solve for the analysis of erbium doped fiber amplifier, or if somebody is want to design the erbium doped fiber amplifier, they are called the coupled equations. So these are called the dP by dz and dPs by dz, so that the propagation of the pump power with respect to the length of the optical erbium doped fiber, and dPs by dz is the propagation of the signal with the z, and they are the coupled because the many parameters in both the equations are common and they have to solve simultaneously. They cannot solve independently. So they sigma Pa is the emission cross section, absorption cross section of the pump, N0 is the erbium ion concentration, Pp of Z is the pump power, PSA is the sigma SA is the emission absorption cross section for the signal. Again N0 is the concentration of the erbium ions, PS is the signal power, W, V and U they have already defined. So they are different parameters. So if somebody is interested, so they were solved for these values. So we have chosen these kind of values for the emission cross section, absorption cross section. Then tau sp is the spontaneous lifetime, n0 is the doping concentration. So this is we have taken from the one of the famous book, Introduction to Fiber Optics by Ghatak and Tyagarajan. So then we have simulated the optical amplifier or erbium doped fiber amplifier using these values. So one can see the results. So the variation of the pump power along the fiber length. So one can see there is a optimum length for a particular pump power. So one can see if the pump power is 3 milliwatt, so it is absorbed completely even at the lower length of the optical fiber. If the 5 milliwatts, so it is linearly decreasing the pump power, and if the pump power is more, so it is again it can go beyond the 7 meters. So this is the like representation, like one can design or one can optimize the pump power, like how much pump power you need for a particular length of optical fiber. So to design a amplifier, we need to have all this. One has to do the simulation so that they can optimize the requirement of optical fiber as well as the pump power. Then we have also shown variation of the signal power along the fiber length for different of pump power. So for every pump power input, there is a optimum length of the optical fiber. So one can see here, if the pump power is 3 milliwatt, there is no gain. So because as one can realize, as soon as we are pumping the erbium ions, they are going to the excited state, and the signal is also coming. So the signal photons, they are inverting the erbium ions from excited state to the ground state. So if the pump is less, so pump absorbed completely, then and signal is also start absorbing with the pump. If the pump is more, so the signal is evolving and it is getting amplification. If the pump is even higher, so we are getting very good signal power evaluation here. So one can say we need to have a optimum length of optical fiber, a particular pump power. Otherwise, if the length is more, the pump power completely absorbed and we will not get any amplification. If length is less, we should best our pump power. Similarly, we have also plotted for the variation of the optimum length with the input pump power. So this is just optimum length increases with the input pump power. So it is a trade-off, one can simulate as per the requirement. Then we have also plotted a variation of the gain with the input pump power for the different fiber lengths. So one can see it's a gain. So there is a threshold pump power for the transparency, beyond which the gain increases with increasing a pump power, and after a certain point there is a saturation. Although you increase the pump power, but gain is not increased because of the saturation. That means there is no more erbium ions available to the pump to send the excited state, so that there is no gain is shown. Then variation of the gain with the output power. So this is also similarly, like if you are increasing the input signal power, so the gain start decreasing because of the input, because there is no more erbium ions available at the excited state for the stimulating of the signals. So the input power itself getting absorbed in the medium and gain starting decreasing. Then in Raman amplifier, tomorrow I'll cover in detail. So today I just covering little bit Raman scattering. As you know, there is two kind of scattering, Rayleigh scattering and Raman scattering. So Rayleigh scattering is a elastic scattering. Raman is the inelastic scattering. So in Raman scattering, when the molecule of the medium is interacting with the incident light, so the scattered molecules is with the different wavelength and frequency, or in other words you can say the energy of the scattered molecules getting changed. But in Rayleigh scattering, the scattered molecule is the same as of the incident photons. So here you can see in the energy level diagram, so when we are pumping from lower energy state, so the molecules of the silica, they are going to the higher energy state, or they are also called the virtual energy states. And when a signal of the same frequency is coming, it is getting the energy from the pump photons and they gets amplified, and the rest of the energy is absorbed in the medium as a phonons. So this is will be, I'll cover tomorrow in the detail when we are covering the optical amplifier, fiber amplifiers, Raman and EDF in detail. In the next section, I'm going to give a introduction, or maybe you can see some of the optical fiber in sensing. So we know like there are huge application of optical fiber in different kind of areas for different parameter monitoring. So the device that detects events or change in physical quantities and provide a corresponding optical output, so they are called the sensors. So they can be used in aeroplane, they can be used for the wind energy, can be road and rail transport, in a building, in a bridges. So there are huge application of this kind of optical fiber for the sensing. So here I focused on the structural health monitoring. So what is the structural health monitoring? In situ, continuous or regular measurements and analysis of the key structures and environmental parameters under operating conditions for the purpose of warning about the impending abnormal states or accidents at an early stage to avoid the casualties and to give the maintenance or rehabilitation advice. So we know like the civil structures such as bridges, dams or buildings are infrastructural assets of the nation and needed to be operative continuously for a very long time under extreme conditions, and hence have to protect it and monitors. Everybody knows through the newspaper in Maharashtra, we know like one bridge was collapsed because it was quite older and not monitored its health. So we need intelligence and smartness in the structures for early warning whenever they are not able to sustain any extra load and tend to give in. So instrumented bridge or building, timely remedial action can be save the structure as well as the huge man and material losses. So there are some of the status how people are doing the structural health monitoring: strict periodic maintenance procedure, regular visual inspection, and use of conventional sensors, that is electrical strain gauges, load cells, linear variable differential transformers, etc. for strain, load and displacement measurement. So here we have proposed and we are working on a different kind of sensors. They are called fiber bracketting. So they are complementing the strain gauges for structural health monitoring. So what is the fiber bracketting is? It is a periodic variation of refractive index in the core of the optical fiber, so which satisfied the phase matching condition, and that is also called the Bragg conditions. And the variation of the refractive index is very small. In the it's a 10 to the power minus 5 to 10 to the minus 4, which leads to a strong reflection of a particular wavelength due to these periodicities, because the periodicity is the order of the wavelength. It's of around 500 nanometer. So when we are sending a broadband light source within a certain bandwidth, the one of the wavelength is reflected back, and all other wavelengths they passes through, as you can see here. So this is the transmission spectrum of a Bragg grating. So the grating is created at exactly this wavelength. Any question? Yes, sir. So they are also act as a wavelength filter. So these kind of devices are very useful in communications. Say for example, the Bragg gratings in communication used as a optical add-drop multiplexer. They also used as a dispersion compensation. They can also use as a gain flattening filter in a erbium dot fiber amplifier. And in sensing, the fiber Bragg grating can be a very good strain sensor, temperature sensors, pressure sensors. They can also monitor the vibrations. Only the thing is we have to devise a mechanism, or we can devise a transducer, so that the strain or maybe the pressure or vibration can be. कोई क्वेश्चन है क्या?
सर काइंडली माइक स्विच ऑफ रखिए अगर आपको कोई क्वेश्चन नहीं है तो.
Continue. So you can see here, if we differentiate this equation, so that delta lambda b by lambda b is giving the sensitivity of this kind of sensor. So it is depending upon the 1 by rho e into delta epsilon plus zeta plus alpha into delta t. So this rho e is called the effective photoelastic coefficient, zeta is the thermo-optic coefficient, epsilon is the deformation, and alpha is the thermal expansion coefficient. So one can say in optical fiber, when we are making these kind of structures, so these kind of structures, they are sensitive for both strain as well as temperature. So theoretically, if one can calculate by using all the optical all the parameter of the silica, like Poisson ratio, then the modulus of elasticity and all those things, so then the sensitivity for the strain is coming 1 to 1.2 picometer per microstrain. It is for the strain sensitivity. For temperature, because there is a two kind of parameters are coming, one is thermo-optic coefficient and thermal expansion. So the thermal optic coefficient is basically the change in the refractive index due to the change in temperature, and alpha is contributing the change in the pitch due to temperature. So how much the change in the pitch due to temperature and how much the change in the refractive index due to the pitch is both they are contributing, and if one can calculate, it is coming 10 to 13 picometer per degree Celsius for the depending upon which fiber you are going to use. Then there are certain features of these sensors. So if you talk of length, so length is basically 5 to 50 mm. They have very strong interaction of mode coupling occurs at the Bragg wavelength. The physics is nothing but, you see, like there is a coupling between core forward propagating core mode to the backward propagating core mode. So the core mode power is coupled back due to this periodicity. Then the wavelength encoded information. So there they don't need any references. Like in strain gauges we need a reference, but in case of these fiber Bragg gratings we don't need any references. Then they are also called the generic sensor because basic sensing is through the generation of the strain. The one of the more important feature of this sensor is they are capability for the multiplexing and distributed sensing. What does it mean is, like many sensors can be connected simultaneously in a single cable. So, and distributed sensing means the different locations can be monitored or detected at a time using single channel. This is our setup at the CSIO. So we have the full-fledged grating writing facility. So this consists of 3 different writing mechanism, like face mask scanning writing, where we are scanning the laser through the face mask and we are creating the grating. Then we have a interferometric writing where we have tall white mirrors and the light is falling on both the tall white mirror. One of the tall white mirror is fixed, another is varying. So by varying the one of the tall white mirrors, we can change the pitch, and due to that we can write different wavelengths. Then point by point writing. So by point writing also one can write the grating by controlling the stage in such a fashion so that it can control 500 nanometer of the spacing. So here like some of the fiber optic smart structures. So by using these kind of sensors, the building and structures can act by their own watchmen. Aircraft, when it is twisted themselves into the optimal aerodynamic shapes, pipeline can be monitored, so that leakage of the pipeline can be monitored by putting these sensors on the pipeline. But smart structures can be able to sense and respond their environment, like where is the bending, where is the crack, if loading in the bridge is more, so one can detect, and timely it can be retrofitted or the remedial action can be taken. We are also working on the biological systems. So these kind of sensor now people are using for biosensing, for the concentration of the different analytes. One can use the glucose and different kind of bacteria detection, heavy metal detections. So one can see the literatures, there are huge literatures available on the biosensing. So to monitor the antibody, antigens, so many things. So I just wanted to show you how the wavelength is changing due to the strain. Here you can see the upper figure shows when the change in the strain due to the tension or compression, so the wavelength is going forward direction and backward directions. Similarly, when the temperature is changing, the wavelength is going from 50 degree to 100 degree Celsius. You can see how it is going to change due to the so they are the signature, basically just a representations, so to get a feel of it. Here I'm showing a fiber grating sensing system, complete sensing system. So like there is a device called the interrogator which is connected with these kind of sensors. So you can see how the distributed sensing and multiplexing can be taking place. So in interrogator it is a 4 channel, so 4 different kind of optical fiber cable. There are so many sensors, and then they are sensing temperature, pressure, different parameter can be sensed, and then they are monitored through the processing units which converting the wavelength of interest, and then the data can be logged and sent to the different location for their analysis. So this kind of system is now we are building, so like it can be used for the real-time monitoring. Then I am going to discuss just little bit of what are the different areas, like in a renewable energy. So in a renewable energy there are the huge blades of these wind turbines, and with the time they are bending or there is a crack in the blades. So if we put these kind of sensors, so their health can be monitored. Then the tower and piles of the foundation can be monitored. The hydroelectric power plants can be monitored. Contaminant system structural health monitoring, leak detection, turbine condition monitoring. So as I have mentioned in the initial, because there is no effect of EMI, RFI, EMP radiation on these kind of sensors, so they can be used in any harsh environment. So the information and signal is not changing due to environment. They have a very good application in aerospace health monitoring. So like you can see, the airframe health and uses can be monitored, landing gear damage detection, unmanned aerial vehicle system health monitoring. So their beings, their fuel tanks can be monitors. Then they have, I have also already mentioned, they have very good application in civil infrastructure. So long-term health monitoring of the bridges, buildings, monuments, tunnels, foundations, road pavements. So these are the some of the examples of the structural civil structure health monitoring. So in the process, we have also carried out the sponsor project from Department of Science and Technology. So we have developed these sensors and we have monitored one of the bridge in the Ghaziabad to Meerut highway. It is situated at the Hapud. So where we have installed at different locations our sensors, and one can see also, because now this presentation is coming. So this kind of sensor we have developed and we have packaged them. So we have two different kind of these sensors, and they have already monitored. They have joined together. So one sensor can be put at one location, another can be another location, and they can splice together, so they can be used in a distributed manner. So these are the like sensor we have developed in the CSIO, and they have already deployed at the real structures, and during the traffic running conditions we have measured their responses. So here you can see here in the second figure. So along with the optical fiber sensor, there are some other sensors also being installed just for their performance comparison. So here at the left side, this is the response of the fiber optic sensors which I have shown here. So these sensors, and the right side, it's a response of the strain gauges. So they are responding equally. Only the thing is, here we have monitored 9 different locations, and these locations was already told by the experts of the structures, because these experiments or this project was carried out with the CRI New Delhi, and they are the basically structural people, so they know at what location we have to install the sensor, so we can get the proper information of the structure. Then we have also developed the FBG based accelerometer. So basically these kind of sensors, they are just measuring the static strain, but if we wanted to monitor the dynamic condition of the structures under the seismic conditions or maybe the bridge vibrations, so we need to have a accelerometer. So accelerometers are available like in the form of electrical accelerometer. So they are either MEMS based and some of the other kind of accelerometer, but here we have developed the FBG based accelerometer. So in this is the block diagram. So we are getting the input acceleration, then we have a mechanical transducers. Can you so we have a mechanical transducers. So one can see here this kind of mechanical transducer we have designed in the laboratory and developed our own, and they are the basically cantilever based. Then there is a fiber brake grating we are putting in these cantilevers inside, and when there is a vibrations, so the cantilever is vibrating and there is a change in the brake wavelength shift, and the vibration can be monitored. So this is the basically 2 axis. I'll show you some of the simulation of these kind of accelerometer. So transducer type I have presenting here, like embedded type, beam plate type, and cantilever type. So ours is a cantilever type. So they are different on parameters, like they have some of the have their good better bandwidths, like embedded is 2 kilohertz, beam plate is 100 hertz, cantilever beam is 180 hertz. But sensitivity wise, our cantilever type accelerometer is better, like it is giving the 330 microstrain per G, and cross sensitivity is less than 5%. So we are developing this cantilever beam type, and since we are developing for the civil structure, so we do not need a very high bandwidths. So because we are working on the lower frequency side, around 1 to 10 hertz. So this is the, you can see how it is working. So the cantilever, so here is the cantilever, and when there is a change in the this Bragg wavelength due to the vibrations, so we are getting the shift in wavelengths. So you can see there is a ASE light source, FBG sensor inside the cantilever, then there is a FBG spectrometer, that is called the interrogator basically, and the FBG spectrometer and data acquisition is the basically laptop with the suitable program. These are some of the results. We have done this experiment at SCRC Chennai using their shake table. So the accelerometer was put on the shake table, and then the vibration of the known frequency was given, and you can see we are getting very nice responses at different frequencies, like it is at 10 hertz at 0.1 G. Then we have basically we have selected some of the frequencies for the presentation. We cannot present all. So then this one is the 75 hertz at 0.5 G, 75 hertz at 1 G, 75 hertz at 2 G. So that we have basically evaluated the performance of this kind of accelerometer at different frequency values and at different G values. So this is the, like at 100 hertz, then at different G values. So we are getting very nice responses without any noise. Then we have also calculated their sensitivity and bandwidth. So one can see, like we are getting the bandwidth from around 10. It's a 75 hertz at 0.1 G. So this is the at the left side graph, you can see that applied frequency versus shift in wavelength. So there is no change in wavelength with the frequency, sorry. And at the right side, this graph shows for the different G values. This is 0.1 G and 0.5 G. So at 0.5 G, we are getting more shift in wavelength. Then we have also worked on our DIT projects, and we have, because as I have mentioned, these sensors, they are very good for the temperature monitoring. So in a transformer, as we know, there is a hot spot. Like this is the distributed transformer, but we have developed this technology for the power transformer, because the power transformer, they have a huge cost, around 1 crore or so. And the thing is, when they are energized, the temperature of the binding of the transformers is increasing, and when the temperature is going beyond the 100 to 120 degrees Celsius, the insulation of the binding gets burned, and there is a catastrophe, and the transformer gets lost, and we are losing both revenue as well as the power supply distracted. So we have developed this technology. As we know, one of the unique feature of this sensor is immune to EMI and RFI radiation. So we know near to the binding there are high magnetic field. So to monitor the temperature, the conventional sensors cannot go near to the binding, so we cannot get a true temperature of the binding. So using these kind of sensors, they are made of the silica, so they are going inside the binding, because their dimension is also very small. and they can be also put in a distributed manner. As you can see, the open view of the transformer, the 3 sensors we have installed at 3 different bindings, and when the power transformer get energized, these sensors, they are reading the temperature, and when the temperature is going to the 100 degrees Celsius, or whenever it is going slightly more, the transformer can be shut down and lets the temperature get down, and then again it can restart. So in that fashion, the transformer can be saved. So this one of the figure is showing like we have also put one sensor in a distributed transformer for 1 year in a Vadodara, and you can see the right side the graph. So we have monitor like binding temperature using FBG. Then to comparison, we have also put the one of the FBG at top oil temperature along with the thermocouple, so that it is showing the temperature of the top oil in the transformer is same, is using the FBG as well as the thermocouple, so there is no confusion, like whatever temperature is read by these sensors, it is right. Here we have also done some of the reliability test of the FBGs at transformers, like we have done with the dates, whether it is the response of the FBG changing with the time or not. So it is not changing, it is almost constant, as you can see in the one of the graph below to the this transformer figure. And this work was carried out in collaboration with the ERDA Vadodara and Elstrom, one of the transformer manufacturing company, and Ardishan Mohali. Then another work we have carried out for the biomechanics application of these sensors. So basically we have monitored the impact absorption capability of the mouth guards. The mouth guards are very important for the sports person, as we know, like in a hockey game, whether it is a boxing, so people are putting the mouth guard to protect their teeth. So if the mouth guard is made with some new material, so we don't know what is the impact absorption capability. So along with the medical college of Amritsar, it's a dental medical college, we have carried out this kind of research where the sensors were installed on the mouth guard as well as the denture, and then we have created the impact at a different wall with the different loading, and we have come up with the conclusion like the impact absorption capability of the mouth guard was found 90% if we are making the center impacts. And this study will be helpful for the better designing of the custom made mouth guard. Like we can, if somebody is coming up with the different materials, so their impact can be estimated. Then fiber based acoustic sensors. So we are working on we are developing acoustic sensors based on the FBGs. So like acoustic sensors are available like Fabry-Perret, Michelson, Maxender, but now we are working on the FBG based sensors. So the thing is, we are making some of the transducers where these FBGs were kept along with the two of the diaphragm between, and when the acoustic signal is coming, acoustic signal is basically a sound signal, and when it is coming, it is vibrating this diaphragm, and due to the vibration in the this diaphragm, there is a strain on the FBG, and the pitch of the FBG getting changed due to the acoustic signal, and one can monitor the shift in wavelength. So where is the application of these kind of acoustic sensors? So one can see the acoustic sensor is widely used in civil and military applications. One of the important application is the hydrophone for the and sonar devices for the anti-submarine warfare. So basically we are working for the hydrophone applications for the ocean surveillance system. Then downhole oil and gas sensing, it can also use for the oceanographic research, crack detection, seismic measurement, ultrasound and blood pressure monitoring, marine mammals monitoring. So these are the application of the these kind of hydrophones. So I have already explained, like the FBG can be put inside a nicely designed transducers where it is glued in between the two properly modeled diaphragm, and when the acoustic wave is coming, it is vibrating this diaphragm, and due to the vibration in the diaphragm there is a strain created in the FBG, and we are receiving the shift in wavelength, and that can be calibrated in terms of what is the power and what is the frequency of the acoustic signal. So in that way, if we can get the frequency of the acoustic signal, we can monitor whether the acoustic signal is coming from the submarine or maybe some sea animals. So they are that kind of application for the sea. Then we have also working on the application of the rail. So the FBG used for the pantograph condition monitoring, because due to the friction in the pantograph and the cable, there is a huge temperature and there is a chance of destruction of these kind of pantographs. So if one can monitor the temperature, the condition of the pantograph can be monitored. The FBG also used for the train condition monitoring, like the railway track, then weight of the wagon, bridge of the railways, train weight in motion, characterization of the rail foundations. All this can be monitored using the FBG sensors. So this is like we have working on these kind of projects. So the thing is, it is already under process. So this is you can see how it is working, like between the different axles the FBG sensor can put on the track, and when the different bogies they are moving over these sensors, so they are according to the weight they are getting their own signatures, and we can monitor the weight of the bogie on a moving train. Because nowadays the trend is, whenever you wanted to monitor a weight of the bogie, it is routing in a separate track and then it is slowed down and then you have to monitor. But if this technology will be developed, then in a same track the weight of the bogie can be monitored. Then I have mentioned beyond the telecommunication and all those things. So then you can see fiber optics is very useful for the biomedical application. So I'm just presenting one of the application is in the endoscope. So use of fiber optics and powerful lenses system illuminate and provide a view of the interior of joints and organs. They are very flexible and different variation of the being different organs. So like they can be designed and developed in a different diameter and with the different capabilities. Then the fiber like amplifier, people are also using making the powerful fiber laser. So the same ytterbium doped fiber can be used to develop the fiber laser. So this is one of the fiber laser developed by US company, and it is already deployed at US Navy to destroy the incoming missiles from the enemy. So they are very good application in weaponry and strategic sector. I found very recently one of the very good application of these optical fiber for lighting up the home using solar energy. So as you can see, there are bundle of fiber, then there is a source of sun, and then we are putting a very good reflector which is focused on the optical fiber, and we have a filters, UV and IR will be filters, and one can also put in between the color filter. So the you can see here how the sunlight, or you can say the natural light, can be brought to the basement or in the room of the any hotels. So there is no need of electricity, at least in daytime, and there is no heating also, because it is already IR and UV filters already put in the system. And you can see how the fiber optic solar lighting is look for a different places. So this is the very good application of optical fiber for the smart cities, smart building, so where we can save the electricity. So in summary, I have covered the optical fiber basics, state of the art optical fiber communication, application of optical fiber for sensing, and fiber optic beyond communications. Thank you. Yes.
Excuse me, sir.
Yeah.
So you told us that the optical fiber may be used to transmit the sunlight
Yes.
from outside into the home. Is it feasible in practical work?
Yeah, it is feasible. Actually, hello.
Yes, sir.
It is already used in foreign countries. In India, nobody is developing, but now we are planning to develop the same system. So now we are already interacting with some of the industry in Indian industry, so that we can develop the same system.
Sir, can you provide the data about the costing of this type of lighting in this home?
Actually, right now I do not have the data, because some of the students from some other IITs also, they have already contacted us, because CSIO is also working on optics. So the thing is, like, if we can design very good reflector, right, we can collect the light from the sun, and then it can be sent using the lenses and the filters to the optical fiber bundles, and then the optical fiber bundles are coming to the home inside the basement and the rooms, and then they are illuminating very nicely.
Is there any company in India providing the material for this purpose?
Nobody is providing in India, basically, because otherwise what you have to do, you have to contact different vendors for the first of all for the optical fiber, but it needs a lot of calculation also. It is not that simple. You have to first calculate what is the numerical aperture of the optical fiber, then how much you need a lens, what is the size of the lens, and all those things.
So, sorry, it is a different type of optical fiber, or the same optical fiber we are using for communication purpose?
No. This is the different optical fiber. This is not the communication one, because I have already mentioned in communication fiber the numerical aperture is very small. Also, the core diameter is very less, so you cannot couple the sunlight to the optical fiber. So they have a larger diameter fiber. They are the plastic fiber, basically.
Okay, so we can use the plastic one instead of optical fiber for the high greater numerical aperture.
Sure.
Okay, sir. Thank you, sir.
Any other question?
No, sir.
Thank you.
Hello.
Yeah.
जल्दी अपनी ऑन कर दिया आवाज आएगी.
Yes. Yes, please.
बोलिए सर, आप ऑडिबल है.
Yeah. We are not getting.
Yes, sir. Yes, at Rajkumar Goel.
हेलो
हाँ सर बताइए
हेलो
प्लीज।
आवाज आ रही है?
हाँ जी आ रही है।
हाँ जी बोलिए सर, यू आर ऑडिबल।
हेलो
यस हाँ जी बताइए।
सर it's quite interactive, your lecture was.
थैंक यू।
And I just want to know that can we not develop a lighting system completely for home and for other users?
No, you can writing system you can develop. The thing is now some of the Canadian companies they are providing a small kind of movements and the lasers and all those things. So then even at low cost you can develop, but not at the home, but at this in the laboratory. But it also cost around 40-60 lakhs. The system which I have presented here, it has quite huge cost. It has around 3-4 crores, but within 40 lakhs 50 lakhs also one can develop the system with the some limitations, like you cannot go for the this scanning face mask technique and all those things, but at least you can write the grating with the small length and all those things.
Okay. Sir, my next question is,
Yeah.
Although the raw material of the optical fiber is quite
What is pardon, I didn't get
the raw material to
Yeah.
manufacture the this optical fiber
Right.
is abundant in the nature.
No, but the thing is the optical fiber for the fiber grating, it is a different fiber. It is not the simple single mode fiber, right?
Okay.
So they are called the photosensitive fiber. They are a special fiber because their core is highly doped with the germania, okay, to enhance the photosensitivity, because people are using the wavelength at 248 nanometer to write these kind of structures. So we need to have a core with the photosensitivity so that the UV can be interacted in the core and it can change the refractive index of the core.
And sir, what are the different companies who are developing the fiber in India? Who are
What are the?
manufacturing the fiber?
In India, actually, optical fiber is manufactured by the Sterlite Communication. It is a Aurangabad based company, but they are making only the single mode fiber for the communication purpose, not for the sensing purpose. And another lab, one of our sister lab at Kolkata, CGCRI, they are making fiber. They have the drying tower, so they are making specialty fiber, but they are also making for their own R&D and projects.
Thank you.
Any other questions, sir?
No, thank you, sir.
Okay, thanks.
Yes, from Kanchipuram we have any question?
So kya? Need a lens. What is the size of the lens and all those things?
It is a different
One by one, please.
Kindly repeat your question, sir.
Yes. No. This is the different optical fiber. This is not the communication one, because I have already mentioned in communication fiber the numerical aperture is very, very small. Also the core diameter is very less, so you cannot couple the
Sir,
sunlight for the optical fiber. So they have a larger diameter fiber. They are the plastic fiber basically. Yeah, for the solar lighting. आवाज धीमा कर दो ना। नहीं आ रही ना?
Hello?
Yeah, please go ahead. Yes, sir.
Hello?
Please,
Hello?
please. Yes, please.
Hello, I am from Balaji College.
Right, sir.
So I want to ask you, what is the is it feasible to use this optical fiber for house lighting?
Yes, yes, it is possible. Only the thing is you have to design the system to couple the solar light to the photon.
Okay, sir. Sir, how much? How many years will it take for the good lighting system using optical fiber?
It depends, like academia and industry partnership. Like if the industry is coming forward, definitely we can develop within 1 or 2 years.
Okay, sir. Okay, thank you, sir.
Okay.
Yes, from Kanchipuram, we have any question?
Okay.
No, sir.
Okay, thank you. If there is no question, I thanks all the participants. Thank you very much.
Thank you, sir.
So tomorrow I'll covering the optical amplifiers in detail.
Thank you very much, sir.
Well,